Morning, everybody. Welcome to the third day of Gaia Alerts. I'm happy to chair the session today on transient and quasars. But before we start, a couple of quick announcements. First of all, please check in when you come in with your signature at the log table on the left in the participation list. If you're not on a list because you're visiting, just put your name below. Another thing, because we have a room for extra meetings back in the IC Tech, if you are there, you might want to come back at 10:30, the latest, because we are taking the group picture. So if you want to be on the picture and look good, be here at 10:30. We will, just after the talk, the last talk, walk outside and to the left. There's a photographer coming by from the IC to take the picture. And yeah, the other thing, lunch will be we will have a slight different lunch time from 1 to 2:30, which is the time when the bus is leaving. So if you have accompany persons, they're invited for the lunch. And please be here at 14:30 sharp, because this is when the bus is leaving. We cannot stop, and we need to leave at that time. So please be here. With this, it's my pleasure to hand the floor to Jeff Kuhn, professor from Hawaii University, to tell us about time domain astronomy with big telescope and the project he's developing here at IC. Jeff?
Maybe this is how I speak to you through here. Okay. Hi. So I'm new to your group. I want to thank Paul for the invitation to talk about this crazy project we call ELF, and to explain, in fact, why this telescope is, or ones like it, are especially designed for time domain astronomy and astrophysics. So a facility which is devoted to time domain astronomy, and time domain astronomy of selected sources that in particular are usually stellar, in the case that I'm interested in. And you're interested, for example, in circumstellar physics, that exoplanets is a special division of circumstellar physics. Then you might ask, well, what instrument or what telescope should you build to be able to do that? And to be able to do it from the ground, because we want to do it in our lifetime, scientific lifetimes. So this was a program that we convinced the European Union was worth research activity a few years ago. And over those last few years here at the IC, we created this program called the Laboratory for Innovation in Optomechanics, devoted to defining a telescope which is specifically for the purpose of what we would call time domain astronomy of selected targets. As such, this is a telescope which is a narrow field of view telescope. Because it's a narrow field of view telescope, there are many, many special properties of the optics that allow us to do things that you can't do with what you think of when you think of the big general purpose astronomy telescopes, like the European and Extremely Large Telescope, or the Giant Magellan Telescope, or the 30-meter telescope. We're talking about a program and an instrument which are beyond those programs. So here's what I'm convinced of. Domain astrophysics science needs a big telescope. By big, I mean the world's largest telescope. By nature, what it does, it's a narrow field of view telescope. And since the most interesting places in the universe are next to other bright objects, it really needs to be something that has significant and high dynamic range. And by that, we mean it has to be designed to be able to paint things next to bright things. And so these are the points that I'm going to try and convince you of. First off, I want to an iconic, which is of interest to most of us. I'll describe that with a few slides. I want to explain to you why this is a problem that should be done from the ground, not from space, which may be somewhat heretical in the ways that most astronomers are thinking these days. I want to explain why it can be done from the ground, why we can do it actually for much less money than we will build a general purpose telescope like, say, the EELT, or the TMT. TMT is now a $3 billion telescope. The EELT is at least $4 billion by the time we finish it. The reason we can do this is that we have now technologies available to us that weren't available years ago when we began the program of creating these other large astronomical telescopes. And then I'm going to show you that we're not completely crazy, and we're actually building a prototype of this right now to be installed up on Teide, and I'll show you some images of that. Okay, so what is the iconic problem that we point to that gets everybody excited and is the reason why we will be able to find resources to build this in the next 10 years? Here's a picture of the Earth. It's real data. It's obtained by NASA, and it shows essentially what the albedo is, the function of position over the Earth. This is data that we use. We put the Earth, say, 5 parsecs, 10 parsecs away. We let the Earth be illuminated by a star, preferably a star which is maybe redder than the sun. And we look at the reflected light from the planet. Now, with any telescope we can build in our lifetimes, we won't be able to resolve the spatial structure on the planet, but we can resolve, for a broad range of stars, even stars that are redder than the sun, we can resolve the light reflected from the exoplanet or emitted from the exoplanet from the star itself. So that's the picture you want to have in mind. If you take that picture and build yourself the right kind of telescope, then the image on the lower left shows the kind of time series photometry you might see due to a planetary object which is spinning and orbiting around the star. And so what you see in that pattern is a daily pattern of brightness created by the albedo variations, spatial albedo variations on the planet. And then you see a yearly cycle that has to do with the inclination of the planet with respect to the orbital plane and the variation between northern and southern hemisphere albedo effects. The image that you see is we had a signal to noise of about 200 in that image, and we used standard inversion techniques. Svetlana Berdugina was the one who led most of the inversion effort. And you can see on the right-hand panel, the upper slide shows what we started with, our exo-Earth located 10 parsecs away. The slide in the middle shows what we can recover, the image we can make, if we can do that kind of photometry. And the lower image shows that we actually don't have to have very high signal to noise in each one of the measurements to be able to make out continents and oceans. So we can make images of exoplanets, and we could look for signs of advanced civilization by looking at the thermal signal, not just integrating the light but by, say, looking at the light at 5 microns versus 1 micron. We could find thermal islands. I don't know if you may know that when you look at, say, the Los Angeles or the California coastline, the black body temperature is a few degrees warmer than the ambient temperature just due to civilization and the effect of the heat that's produced. Heat is produced by any work which is done. So there's a thermodynamic signature for life, which is pervasive. That's the heat signature of life. We don't actually have to know much about the exoplanet. If we just look at the rotational signature, we can derive from the rotational signature using machine learning techniques We can measure the inclination and the orbit and other parameters. And this is just a graph to show you that there's lots and lots of information in the time series that I just showed you. If you have a time series that extends over a period of at least an orbit. What it means is if we really want to do these problems, make images of exoplanets, look for signs of life, look for the spectral signature of forests and deserts, or the heat signature of islands, or photovoltaic farms where the albedo is diminished, then we need a long time series. We need moderate signal to noise, and we need to be able to separate the reflected light of the exoplanet from the star. So here's a slide that makes the point that, let's call it circumstellar science, because we're looking in the environment of a star. We really need a big telescope. We need a big telescope more than the guys that study galaxy correlations or the evolution of galaxies. And you probably know this, but if I started with an aperture of 1 meter versus 10 meter versus 100 meters, and I looked at the diffractive point spread function of that pupil, I would see the 3 different nested curves on the right. So these are a cut through the point spread function, 1 meter to 10 meter to 100 meter, where we have essentially the diffraction created by the pupil, plus we have the phase noise created by the atmosphere. And as long as the phase noise is more or less a constant per area in the aperture, then there's this really interesting fact, which is that you notice the background. Noise background drops like 1 over the aperture squared. Well, that's really good, because that means that as we get to a bigger and bigger aperture, we drop the noise background and we can see fainter and fainter things from the bright star at the center. So imagine that pink is where the bright star lives, and then the brightness in the wings is down to 10 to the minus 8 if we can make something that approaches 100 meters. Of course, that noise is also dependent on the phase errors pattern that you see in the image, and that's the symbol. That's this right here, the phase noise. So if we want to do the contrast problem and we want to look for things that are faint next to things that are bright, we need to control the wavefront noise, and we need to make a really big telescope. Maybe that's not too surprising. So the issue then in controlling the phase noise is essentially how to build adaptive optics in a way which is scalable, or how do we build an optical system which is scalable that allows us to do these things? And that's the magic of what I want to tell you about. I thought it was interesting to look at some of the history of telescopes, because I really like telescopes. I build telescopes. And we're back to the earliest telescope that's used for astronomy. We all know that one. That was Galileo. It really did change the world. Not that Galileo invented the telescope, but he used it for the first time to show how science works, that science is an observational subject. And Galileo established where Homo sapiens was physically in the nearby universe. We learned that we're not at the center of the solar system. We learned that we're at the other edges. We're about, in your generation, to make a similar revolution. Now it's not where we are in the physical universe, but it's where we are in a biological universe. And I'm going to argue in a minute that what we're building fundamentally, observational system, not just to do time series photography, the kind of stars and systems that we're all interested in, but also to break open the problem, make the study of exolife something that becomes an astronomical science. So the question is that in your generation, you should have a telescope devoted to just this problem, because it will change the perspective that we have on the universe biologically. And in a sense, you could think of that as establishing Homo sapiens' place in a biological or a cosmic ecology. And I'll make that clear in a minute. Anyway, all of these telescopes had a significant impact in the astronomical world and in our understanding of of the nearby universe. Really the big step to modern telescopes was, most people have forgotten or don't know, is the Foucault telescope in 1865. That's the first time that we had telescopes that look like what we know about. We used glass. Glass was, of course, known, but glass, the reflective coating that makes mirrors, wasn't known. And that was the big advance that Foucault and collaborators defined. If we look at the last 4 world's largest telescopes, there's a lesson to be learned from that. The Yerkes telescope back in the late 1800s was the world's largest, and you know that that was a glass telescope. It was a big refractor. The Hooker telescope in the early 1900s near Los Angeles was riveted steel. It was soda glass, and it had an accurate balancing system based on a weight that you cranked up, and the weight fell into a long pit, and that was the clock drive that made it track and do the things that we couldn't do before then. The next technology advance was Pyrex glass and the Fourier truss, which you may have heard of, that supports optics in such a way that gravity doesn't create a misalignment in a bad way. And that was Palomar at the end of World War II. Of course, the modern advance that we all think of as Keck, where mirrors were made in a segmented way, and they're roughly 10 centimeters in thickness. Each one of these was the world's largest telescope. Each one of them was a jump in aperture of something like a factor of 2. And each one of them was not a scaled version of the previous. To create something with new, remarkable capabilities in each case required changes in technology. The other interesting point is each one of these was not built by a government. It was built by private funding. The world's largest telescopes have almost always been led by consortia of astronomers, and also at the helm of that organization was somebody with a lot of money who was interested in supporting them. The big telescopes are possible. Here's a 100-meter, and that was built for 0.2 billion. We're not completely crazy. A while ago, somebody paid us money to design something that was a kilometer in size. It's a coherent optical system that the Breakthrough Foundation was interested in. You should know that if you put all of these telescopes together, future telescopes, that the mass and the cost scale like the moving aperture squared. And that's an optimistic prediction. But it means that telescopes like the GBT, the OWL telescope, the Colossus, or the 30-meter telescope are all in the billions of dollars. Each one of these telescopes, especially with the new technology, has a special problem. Once we segment the primary pupil and make it into, so this is an image from with the AO corrected, the diffraction created by edges, because there's a single secondary mirror, is terrific. The speckles that you see are 3 orders of magnitude, and if you're trying to do circumstellar science, we need to get at least 4 orders of magnitude below that. Here's the answer, something called Fizeau optics, and I don't have much time to go through it, but to say that what we do is we build a bunch of independent telescopes and we combine the images. Each one of the mirrors is the same. It's an off-axis parabola. Each one of the secondaries is a tiny little thing that does all the phasing that's required for doing interferometry. And what we do is we interferometry link each of these telescopes with the final image plane. So we look at the image plane to do this. This just illustrates, here's the pupil, and the pupil shows the colors show different phases or different tilts. All of those appear in the image in a characteristic way, and we can use machine learning to deduce what we need to know for the interferometry. So we can take images and call that a speckle pattern. We can run the telescope through machine learning operations. Here's a picture of the pupil. That's a log scale image of the PSF. There's a cut through the PSF. We can now do other things. Because we have a PSF that's generated by the primary and secondary mirrors, we can add phases to the PSF. We can, for example, there's a dark spot in the PSF. It's also called nulling. At so many degrees of freedom, we can produce essentially a tunable PSF. We can produce a coronagraph at the pupil of the telescope, not at the back end optics after the light has already been scattered. Here's a cut through that, and it shows you that the scattered light in that dark pupil is at the level of, well, there wasn't any noise in here, but certainly at least 10 to the minus 8 of the core brightness. So we can do things with this kind of telescope we can't do with a conventional telescope. The self telescope I'm going to show you in a minute, these are models where we built an AO system, a realistic AO system, and we think there's a cut. So 1 arcsecond away, self is a 4-meter telescope, we can get to about 10 to the minus 7, 10 to the minus 6.5 in our ability to look at faint things. Here's where self lies. Self is the small ELF telescope. ELF stands for Exolife Finder. We can see that the self and the telescope we really want to build is over here on the left, the red curves, that we can do better than other both ground and space-based telescopes if we can construct this Fizeau interferometer telescope. Mirrors have to be done in a different way. This is the self telescope design. We create the ideas to build an optical system that weighs much less than anything that we build now by making the structure light. Because each of the telescopes is independent, we can make a light structure and we can produce something which has much less mass and is therefore much less costly. Let's see if I can make this run. That's what it looks like as it will go up on TED. This is what it looks like in the mainland of Spain, where we are building it. And so we've reached the point where the structure is done. One of the mirrors is done through collaborators. And let's see if I could get rid of that. How do I do, Paul? Thank you. That's the telescope we're going to build to do all this. It's called ELF. The first light, the self can have first light in 2 years. That's the telescope I just showed you. We're building partnerships now and creating a consortium to create this telescope, which at 35 meters could be built for about 300 million. A factor of 10 less than what we do for a big general purpose telescope. And finally, the sound isn't going to work. I'll leave this. But this is a description of a. There's a I would say a communion of scientists that believe that life didn't originate on the Earth, that it's a diffusive process. Crick and Fowler, Burbage, and others were big advocates of this. Hoyle, and in that case, the idea that we should find advanced life in the nearby universe is something that's testable and something that a telescope like this would allow us to establish. So this is part of the backdrop to how we will be investigating and finding funding for this big exolife system. So I'll quit here. Thanks.
Thank you, Jeff, for a very interesting talk and view into the future. It's definitely an interesting project. Let's see what we find. Are there questions?
Yeah, David Buckley from the South African Astronomical Observatory. I was just noting that it doesn't seem to have an enclosure.
So the ELF telescope has a conventional dome. It's a clamshell. That's 4 meters, 1.5 meters. The ELF telescope itself, because it's not a very stiff structure, it does need to be protected from the wind. And there's several concepts for that. One of them is that it lifts up from the ground and the ring fits into essentially a donut, and then small roof structures come over that. The dome, in fact, is a limiting factor in defining the final cost of the telescope, and that's something that I think we're trying to be creative with a structure which is extensible and comes back down to decrease the volume of the dome itself.
More questions?
Thank you, Milana Ratajczak, Warsaw Observatory. I have a question about the potential target selection. If the telescope works, what type of stars and what distance from the stars of the planets are you aiming to reach?
So the selection for self, the science case for self is to look for exomoons around brown dwarfs. And so we would have brown dwarfs and binary systems where one of the stars is a solar type star. The Art telescope wants to observe a handful. So within about 30 light years, there's about 50 stellar systems that we would sample for evidence of structure on the exoplanets. And so it would be a 10-year mission where we cycle through these 30 stars to look at their companions and their circumstellar environments. That's a question. The comments that made often is, well, can't we just add a laser guide star so we can look anywhere? That's also a possibility, but we really like to restrict this to the problem of circumstellar environments, but on stars that are interesting. And for the exoplanet problem, it's that roughly 50 stars within 30 light years.
Okay, thank you. And I would like to reserve the last question for me. You said you also can detect heat signatures of civilization. What would be the earliest civilization you could be detecting?
So if the Earth, the heat that Homo sapiens has generated has been increasing almost linearly from Roman campfire times. And of course, as we use more and more power, the power that we use for doing work gets converted into heat. That heat is localized. That localized heat is something that is presumably visible from any civilization. If civilization is diffusive, then we can expect that civilization near to us might be at a similar level of development. At a similar level of development, our hope is that we have enough aperture to be able to see the thermal signature of something like Los Angeles. Now, what that means is that against a thermal background to the Earth, the thing we want to look for is about 3 or 4 degrees Kelvin. So that sets the dynamic range that we need to be able to see in the time series photometry. But the goal is to be able to see something that's more or less like, and it's possible for a civilization which is more advanced, using more. It should be easier because the it is a very high albedo transition from continents and the things that look natural. So it would be an unnatural geometry that we see.
Thank you. We thank Jeff for a very interesting invited talk. And we continue with Priscilla Pesci on an additional invited talk on AT 2022 and the challenges of classifying luminous, long-lived, hydrogen-rich transients.
Okay, good morning, everyone. My name is Priscilla. I'm a postdoc at the Oscar Klein Center at Stockholm University. Before starting, I would like to thank the organizers for inviting me here to this very interesting, very diverse workshop in this amazing venue. Today, I will tell you a story that is further away from life and closer to energetic things. And it's the story of this one object, 2022 ACME, or as you may know it, Gaia 22 DMP. Okay. Okay. Before, I need to make 2 disclaimers. The first disclaimer is that this workshop is Gaia and Black Hole Tone Center. Gaia and black hole time are not main characters in this story, but they are necessary characters for the past and the future of this type of transients. And the second disclaimer is I have changed a little bit the order of events of the story just for dramatic purpose. So anyway, so this is object I selected to display the challenges of classifying luminous long-lived hydrogen rich transients. And when I say classifying, really what I want to say is understanding the physical mechanism that drive this type of transients. And why I selected long-lived hydrogen-rich transients, because I do supernova, so my main topic of research is supernova, more specifically hydrogen-rich type 2 supernova. And I was studying a particular subclass of type 2 supernova that are hydrogen-rich, superluminous, so very energetic objects from the Suki transient facility. And I was studying this sample, trying to find similarities, but also the odd objects within the sample. And I find things that have multiple peaks, things that take too long to rise, things that take too short to rise, things that take too long to decline. And then I ran into this one object. And that was discovered by Gaia. So here you see how Gaia was necessary for this particular story. And when it was reported as a supernova candidate. And if you look at the galaxy, this is not working, but maybe this works. So yes, so if you look here, these are the stamps from CTF, and in the middle, you can see the template image, so the historical image of this object. And you can see the science here, and you see the bright transient that appears in the difference image. So you can look at this, and if you have studied supernova, you see, okay, yeah, this looks like a supernova. Let's go classify it. So again, classifying it means understanding what type of processes are producing this event. And so a spectrum is taken that you can see here. And you can see in the spectrum, these vertical blue lines are hydrogen emission lines. And because these lines are there and have this particular narrow appearance, and then this event is classified as type 2N supernova. Type 2, because it has hydrogen, N, because the features are narrow. However, these narrow features, what are indicating is that we are not actually looking at the supernova. We are looking at the interaction between the supernova ejecta and circumstellar material that is in front of the star before it explodes. Supernova is an explosion of star. So a star explodes, find this material in front of it, and then we see this type of emission. So a lot of people don't really care. So this was classified as type 2N and then a bit forgotten. Until 2 years later, when another spectrum was taken, and then this object was reclassified as ACN based on the presence of forbidden oxygen 3 lines. And here, the reclassification is very important because now it's not a star that is exploding anymore, but it's an ACN, meaning that it is a supermassive black hole that is accreting material. However, if you look at the spectrum a bit more closely, these are the forbidden oxygen 3 lines, and you can see that this line was already present in the first spectrum in orange. And how we classify is by spectral matching. So we take a spectrum and we compare it to previous spectra of classes of events. And so the new spectrum will also match a type 2N because it's very similar to the first spectrum that matched a type 2N. So then we look at the light curve, and this was the light curve when it was first classified as a supernova. And you can see it's rising and declining supernova-like. This is GRI bands from CTF. And this is the light curve 2 years later when it was reclassified as an ACN. So, okay, now with the spectrum, the new spectrum, and this light curve, you can say, okay, this looks a little bit less supernova-like and more ACN-like. However, I'm a supernova person, and I was convinced this was a supernova, and in particular superluminous because it reaches a peak absolute magnitude -20. So I want to dig into this and try to understand whether it is a supernova or an ACN, and I was really convinced it was a supernova. So as I say before, the two scenarios were exploding star, accreting black hole, but if you are talking about black holes, we also need to consider another energetic processes that are tidal disruption events. That is the disruption of a star when it goes too close to a black hole. So now we have these three physical scenarios and one single object, and then we need to fit this one object in one category. So let's look into this. So this is the light curve and the historical light curve that you can see here in the left-hand side, sorry. In the top panel, you can see the historical flux, and it's doing nothing, and then it suddenly bursts. And when you see in the bottom panel, the absolute magnitude, you can see that it's not very well followed up, this object. It has several gaps. Luckily, we had Gaia that is filling in some of the gaps. So again, it was necessary to have it because then we can interpolate this historical light curve with some more confidence and try to derive parameters. But you can see, particularly the most interesting part for me in this case, that is the peak is very poorly followed up. And we only have Atlas data for them. And then we took a series of spectra. So we have this spectral series that I don't know if you see, but it spans almost 600 days. And the spectrum is doing nothing. It's just emitting these narrow hydrogen lines for 600 days. That this could happen in a supernova if the circumstellar material is very dense. It is not unlikely. It's not impossible. So we look into the spectral lines in the right-hand side. And we see some very energetic lines that are typically called coronal lines. And okay, these lines appear in ACM and TDEs, but they also can appear interacting supernova. And then we look at the energetics of the light curve that you can see here on the left-hand side. This is a pseudo-bolometric light curve. So for these, as black dots, you can see GRI band. So you get the SED of this, considering these bands, you get your pseudo-volumetric light curve, and then you try to infer what is the total radiated energy of this object. It's a lower limit, but at least it gives you some information about the energy that it's producing. And we get some number if we don't include the peak. And if we consider the peak, that is a very, very rough estimation because we don't have colors, so we only can do a volumetric correction to the Atlas light curve, then we get higher, of course, higher total radiated energy, but still within supernova limits. So still can be a supernova. Let's look at the host. Because if it is a supernova, the position of the host, of the transient, sorry, is far from the center. So it's unlikely that it is an ACM or a TD. Or if it is an ACM or a TD, then it's very interesting because it's off center. However, if you look into archival images of the legacy survey, you can see here in the center that everything that is considered a host originally was considered a host is encircled in this green area. And then if we take the regions of constant intensity, we see two different closed regions that this cyan that now from now on I will call galaxy A, and this orange that I will call galaxy B, indicating that there can be two different nuclei of in this environment that we are observing. And if we look at the colorized image here, we can convince ourselves, okay, this is actually two galaxies that are merging because the morphology of this galaxy is a bit odd. And now our transient happened in the center of this galaxy B that I mentioned before. And now because it's in the center of a galaxy, it's more reasonable that, or more likely that it could be associated to a black hole. And now my hopes for it being a supernova disappear a bit. And then luckily, we also archival data. We have a DESI spectrum of galaxy B. And then we also observe galaxy A. And if we look at key spectral features are H beta, the forbidden oxygen 3, and H alpha, we can see that especially the forbidden oxygen 3 of a galaxy B and galaxy A are very different. Again, classification we do by comparing with objects. So I decided to just compare with everything that is a supernova, an ACM, a TDE, a spectra, and light curves. And I see a lot of similarities. Okay, this is qualitative. Let's see let's see numbers, sorry. And when we see the numbers, the way how you can find an AGN is by placing some measurements in the VPT diagram. And we can see that the galaxy V falls nicely in the AGN region, galaxy A in star-forming region, and then our transient is all over the place. And then when we compare H alpha over H beta parameters with TDs and supernova, we see our guy here in black doesn't really match TDE and doesn't really match supernova. And when we see the velocity, we have maximum velocity of H alpha. Again, in gray, there is TDE, not really. In colors is supernova also. Could be, but also falls in this pink region that is of changing look AGN. And changing look AGN are AGN that change its look. That can go either from quiescence to activity or from a type of AGN to a different type. So this is our conclusion that this guy was a changing look, is a changing look AGN that is mimicking a supernova, and it was triggered by the merging of these two galaxies. So I talk about this one guy, but how do we move forward? How do we better understand this type of transient? So Gaia was an alert machine, and our future alert machine will be LSST, which is the Legacy Survey of Space and Time, that is in Chile and will be scanning the whole southern sky with a big cadence in different colors, and it will produce millions of alerts per night. So we will have many more of these objects. And in case you were wondering, the background of my talk is the first look of Rubin. So this is the first image that we already obtained from this observatory. So for the longest time, we were waiting for it, and now it's here. So now we need to be ready and need to prepare for it and need to understand how we are going to process this amount of targets that we are going to get. In particular, for my targets, the ones I'm interested, we need to consider other wavelengths. And because I do energetic transients, X-rays are important. And in the story I was telling you, X-ray was important because we got an Rosita spectrum and we could model it and also obtain hints of it being an AGN. We need archival data to know about historical activity, and here Gaia can be very useful. And also we need coordinated follow-up to avoid missing key features in the light groups. For example, in this case, I missed the whole peak. I don't have colors. And I want to emphasize this because I was doing superluminous supernova, and to know it's a superluminous supernova, I need to observe the peak, and I need to know the peak absolute magnitude. So I was thinking, okay, I was working with CTF, and I was trying to figure out, okay, how are my light groups going to look like on LSST? So I use the operation simulation of LSST to know the cadence. What would be the cadence of observation for my objects? So I took objects that are in the overlap footprint. Although LSST is in the south, it has some coverage of the northern sky. And these are air mass limited, so it's good quality. These objects would have been observed with good quality by LSST. And I check what are the light groups. So in dim circles is CTF, and dark stars is LSST. And okay, I already can see that I miss a lot of peaks. So when I look at the distribution of peaks I will obtain by LSST, that is this dark distribution here, I miss a lot of peaks. And you can say this is an unfair comparison because LSST will have more colors. Okay, but I still want a pseudo-volumetric light group, so I still want my peaks to be observed in several or more than one color. So here is where our black hole tone becomes very, very important because it can allow us to fill in the gaps. So for example, if you see here in the top, this one light group that only has one point in the R-band could be followed by a facility like black hole tone. Also here, we have another object that is only has the very rise, but the whole peak is missed. And as you can see here, you have, sorry, this is not absolute magnitude, it's apparent magnitude. And in apparent magnitude, these objects are not even that faint. LSST will reach high depths. but it will also discover a lot of brighter events. So even if this object was a bit dim, around 20th magnitude when it was discovered, then it became brighter. So BH-TOM could be a very good facility to observe. And I don't know if you noticed, but I have shaded this map of the distribution of the telescopes of BH-TOM, because I think it's very important to consider that BH-TOM has telescopes in the south, which is where LSST will be. So although there is some overlap between north and south skies, it's very important to have southern telescopes to observe southern targets. So with this, I reached to my summary. I hope now you are interested about ambiguous transients if you were not before, which is what I am interested about. I think that having events that we cannot classify means that we don't really understand physics in these cases, particularly things that are associated to black holes. And then we need to move in the future knowing that we will have a great machinery that will discover many of these type of transients, but with some limitations. And then we need coordinated follow-ups, and BH-TOM is a good tool for this. So thank you.
Thank you for a very interesting talk. And well, you put a invited talk into a very good time frame. Thank you for that. So we have time for questions. And the first one is from Lukasz.
Hi, Łukasz Orzechowski, Warsaw. Thank you, Priscilla. So coming back to your curious case, so you showed the map of the host and then where you identified, yeah, this one. So I was wondering, could you comment on the X-ray and radio locations? Because they're not associated to any of the galaxies. And maybe they're inaccurate, but can you comment on this? AGNs should be X-ray more active, right?
Yeah, so the thing is the beam, let's say, of this telescope. So the pointing, for example, for Rosita was here, which is basically in the middle, and this is the, let's say, the error. So this circle is the error associated to the observation. So it actually encircles the whole thing. And so for us, having at least a hint of a possibility of an ACN was meaning that at least there is some hint of an ACN presence in this whole area. And then you said, sorry, for the other wavelength, for radio. So yes, we have radio observations. So we had stacked images, and we could only observe radio signal here in this area, and we could not observe radio signal anywhere else. So this was still when I was convinced it was a supernova. But you can have ACN that are radio quiet. So.
Thank you. Fantastic result. And I knew nothing about this until this meeting. So, and the Hinkle is calling them ENTs. I think you prefer ANTs.
Yes, there's a Phil Weisman that is say ANTs, and I share the ANT.
ENT sounds like ear, nose, throat, which was uncomfortable for me as a child. So I do have a comment.
Yes.
Which is the Gaia light curve we produced. I had no idea it was going to turn into this. We actually see it's flat all the way back to 2015. So it extends beyond what you showed us was flat to 2017. But there's another couple of years of Gaia data on our website. So it shows it's flat for even longer than.
That's great. Yeah, and because I wanted to show the flags here and I didn't really know how to get, sorry, flags from Gaia. This is why I don't show it in the flags, but I show it in the magnitudes. But okay. Yeah, thank you.
I can help with it.
Yeah,
you want to do that. Sorry, Simon Hodgkin, Cambridge University. Many thanks.
Thank you.
Thank you. I just wanted to remind people to say the name and affiliations, in particular for the folks on Zoom. Thank you. Do we have another question? Yeah.
Hi, Nada Ihanets, ING. I might have missed it, but what if this is a nuclear transient, right? If it's AGN or TD, what's the mass of the black hole? Where did you determine it, or was this analyzed?
Yes, it was. I didn't put the numbers here, and I don't really remember the number now, but it would have been consistent with the TDE. So it was not a supermassive black hole; it was an intermediate mass black hole. Okay. Based on our calculations. Yeah. It's in the paper. I don't remember exactly the number, but
okay,
yes.
Just out of curiosity.
Yeah, but it was calculated.
Yes. Okay.
Okay, one final question. If not, we thank the speaker again.
Thank you.
And our next speaker is Marusz Rodemski. Thank you. Warsaw University. I see we have a Polish majority here. Very good to see people coming to the island, and I hope you get to enjoy the island a little bit. So just to say, the weather here is not Tenerife, that's La Laguna. And we call it also Mordor because it's always in the clouds. So with this, we'll put our head up back to sky. Stage is yours.
Hello, my name is Mariusz Gromacki. I would like to say as most of the speakers before that I am a PhD student or postdoc, but it's not true anymore, unfortunately. So I was lucky to meet Łukasz like 10 years ago in Las Campanas. It was your last run for Ogla, I think. And two days later, Łukasz offered me the job. And I start a huge adventure. Before of that, I'm not doing the transient, I'm doing the different things. I'm doing the symbiotic stars, why I have to read the paper of the Jarosław from time to time. I'm doing the brown dwarfs astrometry and near infrared photometry as well, spectroscopy. Oh, I have the huge background with working with the observational delta in many techniques, so I was perfect candidate for the Łukasz to give me the job. So, and the Łukasz opened me a lot of opportunity. I joined a lot of collaboration. You have the list here. Okay, and I even was involved in a little bit in the black hole tom. I write the module of grabbing the WISE data at some observatories and stuff like that, but I work for Łukasz, not work for Łukasz, work for Łukasz, and now I'm not work for Łukasz. But Łukasz asked me to, Mariusz, could you take care for these targets? Supernova 2023 IXF. This is the closest supernova within the last decade, and in this feature we don't see these things because Jarosław asked to send the PDF, the animation in the original, and supernova is here. Okay. Okay, it's good to remind some basic facts about the supernovae. As Priscilla said before, the supernovae are the explosion of the stars with massive stars, or the ignition of the white dwarf, which then merge or accrete the masses. And this is the finish, the life of the star. In case of the massive stars, we have okay. We have the product black hole. All the neutron stars depend on the mass of the object. Depends on the interaction masses and things like that. And is it the white dwarf or the massive stars? We distinguish different types of the supernovae. Here you have. Okay, sorry. Okay. I think I have to press this one. Yeah. Sorry. You can distinguish different types of the supernovae with the different evolution. This is the classic plot from the Filipienko review from 1997. And what is the important thing? The supernovae are very bright. Here you have now the magnitude or Planck scale. But supernovae 1A, they are like 19.5. The supernovae type 2, they are like 2 magnitudes fainter. And the magnitude range now is much wider. You have the underluminous supernovae, which is like 12 and a half YAX supernovae. And we have this superluminous supernovae, which are brighter than minus 22. Priscilla mentioned about that. Okay. So studying the supernovae is very significant because they provide the heavy elements, heavier than the iron. They are the elements essential for the technology, essential for the life. They drive the ecology of the galaxy, enrich the interstellar medium, trigger the new stars, and things like that. They are very important things to measure the distances of the universe and study the cosmology of our universe, especially type 1A. I have to back to here. Okay. I would say that in case of the supernovae 1A, sorry, typical supernovae type 2, which is the IXF, it is brighter like 500 billion times than the sun. This is the scale we talk about. Okay, how looks like the pathway to study, discover the supernovae? Nowadays, I have the plenty service like Assassin, like ZPF, go to other one, Atlas, and all of them use the differential image analysis to discover the supernovae. We have the template, and we have the current observation, subtract one from each other, and we then see clearly the new targets. Then we report these targets to the transient name server. People from take the information from the transient name server, and they trigger the spectroscopy, and they got the classification spectrum. Then report this classification to the TNS again, and it depends if the object looks interesting or not. The people decide to follow up. Usually using the big telescope for the spectroscopy and the smaller one for photometry. And after a year or two, they finish usually after half a year, they finish the follow-up, and a few years later appears the paper. Okay, this is the way. And we can ask, is it the small telescope are suitable for the study of the supernovae? They are very suitable for the photometry. Definitely, they are more economical to use the small telescopes to get the photometry. But it's almost impossible to use them or take the spectroscopic observation. And here we have the distribution of the brightness of discovery. Unfortunately, the TNS not provide the information about the luminous brightness in the peak, and we see, but we can just shortly scale in this direction. I don't like the mics at all. Okay, I try to use the mic. I don't like use this device. I prefer the natural voice. Okay, so if we shift this one in left, we will less more have the distribution close to the maximum peak. For example, this IXF in the maximum was 10.8 magnitude. Okay, so this is the observation. I decide to plot that as it is in the black hole tom. I do the tuning of the data, removing some minor issues from the things, but for this reason I plot this one, and here we have almost 7,500 of points. 4,500 of these points was taken by Staszek Zoła, which is somewhere there. And there was used the bands from UV to the mid-infrared. Here we have the light curves taken by Swift telescopes. Here we have plenty of the optical follow-up, and these points here are the points taken by the WISE telescope in 3.5 and 4.5 micron. Okay, so what we can do with this data? I have two ideas. First idea is just estimates how many energy we have, making them a bolometric light curve, and we also can estimate the temperature evolution and things like that. And this is the example by Takashi. He used the previous data. Here we have like 800 days. Here we have the dates from the calendar, but this is like 800 days. Here's the preliminary dates. This is just like 3 months, and they fit some models, and it allows estimates to get some parameters of the supernovae, like the mass of the progenitor and the mass of the interstellar matter around, and the mass of produced nickel 56 and things like that. And this is definitely what we did with this data. And the other idea to is the looking for the rapid variability. And here we have some example. The left side, we see the paper written by Bananos and Bumis for the supernova 2014J, and they do the fast photometry in the different band. But this light curve, they are the differential light curve, and the same type of the work was this is with the Aristarchus telescope. This one was with the Sinacas telescope, and this work was repeated for the other object by Emily Parscaves. And we can do the same because the data collected by Staszek, okay, just finish the data collected by Staszek. There are the series that is taken in the series, especially close to the maximum of the light curve. And here we have the example in the V band. You see that this is the 11.3, and at maximum was 10.8. So this is quite close to the peak, and it's covered like 4 hours, 200 points. Unfortunately, I don't know how to download the data of the neighbor stars to make the subtraction. This is like the points only for supernovae, and we see that there is the scatter, and maybe when we remove the light of the neighbor stars, we will see the smooth changes of the light, not just the noise. Okay, and this is my takeaway question, but I chat with Łukasz before, and he explained me that this is the way to obtain the photometry of the all stars on the images taken, uploaded to the black hole tom. Okay, this is all what I want to say. Thank you very much.
Thank you for the talk. Are there questions?
Since I was called to answer this, so indeed there is a way, and Mariusz, you're cordially invited to our hackathon on Friday. You'll learn how to do that. All right. So, but we can do that as part of the hackathon with other people as well, and have a recording for you delivered so that then you know how to do that, and then at the same time other people can also learn how to do this. Mm-hmm.
That was also a gentle reminder for the hackathon on Friday. I'm looking forward to it. Are there other questions? So then I have one. You showed serious time series of photometry. Was it 800 days, several thousand data points? What were the challenges for you to put everything together?
This is actually not a challenge, because you can just go to the web page, and you press the button. You go to the web page, press the button, and you have data on your computer. Later you have to separate, because you have like a huge table. It is sorted by the dates, and of course you want to sort it by the you make the separate filters file. And the challenging thing is you see that you have to look carefully on this data, because you have some issues with the weather here in Kraków. So you have to remove these points, and there was some reductions issues, and I asked with the Łukasz, and we just repeat the reduction process, and it should be much better than it is. And there is no much work. This, as Łukasz said a few days ago, it's almost ready to analyze.
Yeah, just a quick question about the model fit that you showed. I mean, you said this 2015. I guess it's 25 maybe, because otherwise that supernova was later.
2000.
Yeah, this one. Yeah, I mean, I look at it, looks like a bad fit to me, but I don't know other people. That I don't know how convinced you are that the parameters that you derive from this fit are okay.
So generally, these parameters are what the other authors got it within the errors. And so we have the observation of the progenitor, because the galaxy is quite close. So we know that the mass was in this range. So more or less, I think this is the best fitting.
But then how
others, they use the grid.
The difference in the light curve shape. So one has like more hydrogen than the other one. Is that like the?
Yeah, this is the question to Takashi, not to me.
Yeah.
Okay, I can ask Takashi and back to you later. It's 2024. Yeah, this is the mistake. Yeah, 2024. Okay.
Then we thank the speaker again and welcome the next speaker, Andrea Simonini. And he will do that, okay, great. And he will give actually two presentations. First, we will have a poster presentation on not all the tridents are fiery. I'm looking forward to that. And afterwards, the contributed talk on Core Lab Supernovae.
Okay, thank you.
Stage is yours.
Good morning, everybody. My name is Andrea Simoncini. I'm a PhD student from Rome. And yes, this first contribution is again about superluminous supernovae. So I'm very happy that this was already introduced by my colleagues. And what I wanted to talk today was this particular event, 2024 JLC, which, you know, from previous talk, you learned that superluminous supernovae are usually the peak luminosity above -22. So when this supernova was classified as a superluminous and it reached a absolute magnitude peak of -19.2, it raised some concern. So this is my preliminary analysis of this object. I'm trying to understand what it's really happening, why the luminosity is so low, and why we can still classify it as a superluminous event. Of course, you don't only rely on the peak luminosity. There are spectral features that are common to superluminous events. There's spectral matching with other objects. There's also the behavior of the entire light curve. And in the end, what it's really looking like, it's very, very similar to other superluminous events, but it's underluminous. That's why I called it like that. And well, I don't really have much more time to speak about this thing. We performed a multi-wavelength analysis, and the current preliminary results are pointing towards having a helium-rich supernova, and this might be a hint of why it's underluminous, because in literature, other superluminous events that showed helium lines are also the ones that are less luminous than the others. So that might be an hint. And also the upper limits that we could obtain with X-rays and gamma rays are actually pointing towards a circumstellar interacting kind of powering process. For superluminous event, we usually think of a magnetar powered event. So that may be another hint. So just to say, this is very preliminary. I'm currently working on a new data set in collaboration with the ZTF. But if you are curious and you want to talk more about this later, you can come and find me at the coffee break. And thank you.
Do you have any comment, or please?
Hi, great to see another superluminous supernova. Priscilla from Stockholm University. Maybe this is a very naive question, but have you checked the extinction?
Yes.
It's not very extinct.
So we checked. Currently, in the new data set that I have, there are also some host galaxy spectra, and that will help much more. The current view is that the extinction from the host galaxy is almost negligible, and the galactic extinction is already taken into account. So yes, the extinction is not taking a huge role in this. But thanks for the question.
Some more? Well, we have time to discuss after your next talk.
Nice.
And we are good in time, so we probably have some extra minutes for coffee then. So.
Okay. Nice. Okay. Good morning, everybody. My name is Simoncini. and I think that now you will remember. And let's change a bit the topics. We are still sticking supernovae, so things that explode like the last 3 talks. But now let's have more details on the LSST survey that was already introduced by my colleague. So I have more time to talk about my work. Thank you. But let me just give you some little bit more details on what this new survey it's gonna do for us and for all the people in this room. In general, the LSST survey is also called the greatest movie of all time. It's starting late 2025, late November, hopefully, and it's gonna take 10 years of continuous data every night from Southern Hemisphere in Chile. And well, these are some numbers of the survey. 18,000 square degree region observe almost 32 trillion observations and 20 billion galaxies in 6 filters from near UV to near infrared, with a final depth of 27.5 magnitudes in DR. So it's gonna be very good also for very faint objects. And in particular of my interest, well, LSST was developed for many scientific goals, but one of them was transient events. And I'm happy for this because I do supernovae. And for supernovae, what we expect from the LSST survey is that we are going to detect and discover 10 million supernovae. So it's almost 1 million per year. And this is unprecedented. This is more than 3 orders of magnitude or even more of what we know so far. But of course, these 10 million supernovae, like it was showed before, are also like a single point in a light curve. So it's just a discovery, not something that is useful for science. But out of these, 14,000 at least will be in high details, which means more than one filter, a lot of data, a good coverage in time and cadence, which is again more than 1 and 2 orders of magnitude of the very good observed objects that we have today since the beginning of astrophysics, basically. So it's going to be an unprecedented opportunity for all the sciences and for supernovae people to characterize progenitors of known and peculiar supernovae and do a lot of new science of this. So the first image was already shown. I just wanted to show you that the LSST survey is already providing new insights in transient events. Unfortunately, during the first look, they didn't show supernovae because they prefer to show stars. I can understand it. So this is just an idea of what Vera Rubin is already doing to discover transients. And in this case, they discovered 3 variable stars in different images. But if in the middle column you remove light, you basically have what they are going to do with supernovae. And by the way, this is still, I think, not public, but they are already discussing on it. There were some supernovae also in the first image. You just have to look right at them. Okay, so let's focus on what I did for Vera Rubin. And in particular, when you develop a new survey, when you have new ideas, it's always important to build a good telescope and always important to understand your scientific goals. But then in the end, the scientist needs to be aware of the good quality of the data that we'll collect. So the question based off this work was how good the data of Vera Rubin for supernovae will be and how will they allow us to characterize properly an event to make science out of it. So this is what we did. We simulated light curves of type 2P supernovae and analyzed them, knowing, of course, the original parameters from the simulations and the parameters that we estimate empirically from the light curves. And by comparing the 2 distributions, we are able to say some things about the quality of this survey. And in particular, we are analyzing almost 7,000 2P supernovae, which is a realistic number comparable to the actual number of 2P supernovae that we expect at the end of the survey. So a little bit of details on this. So as I mentioned, the data are simulations, every supernova distributed in a 3D space in redshift and extinction. And of course, it has a different cadence of observation. Every magnitude limit is taken into account, and also the saturation, which, spoiler alert, is going to be a huge problem. And every light curve is interpolated without taking into account any model. It's data-driven interpolations. Then for the analysis, we use this software Castor, which estimate all the parameters directly from light curves. So it's very helpful. And it's basically based on 3 steps. The first one is a comparison. So we do comparison matching with the literature that we have so far. Then we build some synthetic spectra. And using all this data, we can estimate the parameters using very, let's say, simple models, not to introduce too many biases in the analysis. And this is how our light curves look like. So this is just one random supernova in all the sample. And it's actually a pretty good example because it has many of the features that we will also have in the LSST survey. So for example, some of these filters are saturated and we completely miss the data in the peak luminosity, and this is a huge problem, as was already mentioned. Some filters don't really coverage the linear decay phase of a supernova, and some are basically just stopped after the first 50 days. And this is more or less what we expect from all the supernovae during the survey. So the question is what we can do with those data. Once we have completed the analysis, we have to use some statistical figures of merits to understand the quality of the estimation. The first one is this KL divergence, which basically identifies the difference between 2 distributions and is telling us how good one distribution is an approximation of another distribution. Well, the second figure of merit is FOM, and it's basically quantifying the relative error of estimation for each of our parameters. So let me show you some results. I don't pretend that you have a proper look at every plot that I'm showing. Just let me comment on this. So in this first plot, you just see the distributions of the true parameter that come from the simulations and the observed parameters that we retrieve from our analysis. While in the right table, you see the final results. So these numbers are on a scale from 0 to 1. And if it's in this scale, it means that it's a good estimation, while if it's above 1, it means that you start having more and more problems. So for example, for distance, we have 1.2 in the KL, which means that there's some problems in the reconstruction, while for example, for the mass of the progenitor is a number below 1, which means that we are actually reconstructing the mass with a good error. And another very important thing is this huge plot. Again, don't mind looking at everything here. So this is how the error of estimation behaves in terms of different parameters of the event, which are redshift, extinction, cadence, number of filters, and peak luminosity. And for example, what we see from this is that high redshift means high errors, and automatically also high extinction means high error because they are connected. While for the cadence, a good news is that for these good events in which we have a cadence between half a day and 3 days, using interpolation, we don't really suffer from a different choice of cadence. The number of filters in general, it's better to have more because you want to reconstruct a bolometric light curve always. And also the peak luminosity, it's well connected to saturation, so also that it's producing errors. So this is, don't understand this, don't worry, but the conclusions is this that you can retrieve from that. So the first main result is that the saturation will be a party killer for everyone, especially for supernovae people. Vera Rubin is not built to observe things that are in our galaxy or in the surroundings. So we already know this problem. While for high redshift, well, we will probably need other techniques. In this case, we're using spectra of supernovae, but to estimate the redshift of very far events, there may be the need of using other objects. I was in a conference and they were discussing about using AGN association or things like that. Then, of course, number of filters, if it's limited, it leads to underestimation of the bolometric light curve and so the energy. And in general, the main result is that LSST is going to be fantastic. It's going to be a very game changer in the next 10 years, but we don't have to forget that it will not suffice for a perfect characterization of every event. So we need a global network, and that's why I'm here. But all in all, we can also say which going to be the best supernovae for us. So supernovae in the range of redshift 0.01 and 0.1, so in the Hubble flow, with an average extinction and the peak luminosity, these are going to be very well analyzed with the data from LSST survey. And well, I'll leave you with this slide. And if you're more curious about this work, please have a look at the published paper, and I will be happy to answer all your questions. Thank you.
Thank you. Questions? While people are thinking about the question, oh. Okay.
Yes, I was curious about the cadence of LSST. Is it defined? There was this opposition between observing at the meridian, or so what can you say? Because you used simulation, so you based your study.
Yes, on the cadence. So our simulations, thank you for the question, by the way. So our simulations are, let's say they want to simulate the base cases. So the ones that are gonna be observed with a more or less regular cadence. So in fact, the maximum cadence that we have that is shown here, it's 1 point every 3 days in at least one filter. So this is for all filters. So at least one of 6 filters has a point 1 every 3 days. But the cadence is not fixed for every event. It's gonna be, it's depend on where the camera is looking at the moment.
Yes, if I'm correct, it's not only a question of limited number of filters, but there will be no simultaneous color because they use one filter at a time. So in the early phase, particularly in the raising phase of the supernova, it's quite damaging to understand the physics if you don't have simultaneous colors.
So as far as I know, the filters selected for a night will be 5 out of 6, if I'm not wrong. But yes, it's of course they're gonna change every filters from time to time. Something that I didn't show, but we checked following your question was also which filters is it better to have a better reconstruction than others. And what we saw from this analysis is that it really depends on the phase of the evolution. So during the first early stages, if we have filters of U, GR, it's better, while in the late stages, we prefer the infrared filters. So yes, of course, it really depends of when you look at a certain filters and which filters do you have.
Buckley, South African Astronomical Observatory. Just as a clarification, I think it's unlikely to be more than 2 filters in any given night.
Mm-hmm.
And those observations are likely to be quite well separated, like ours.
Okay, thank you.
Constanze Sedelska from German Center for Astrophysics. Did you have a look into the neutrino signatures that could help you identify those events?
The neutrinos?
Neutrinos.
No, honestly not.
Okay, because with I think the denser arrays for KM3net and IceCube, you maybe could get something. They have a supernova monitoring programs running. Just a remark, might be interesting.
But
to do with multi-messenger.
Yeah, I mean, of course, but I make a question to you. What is the detection horizon for these neutrinos? Like here, we are talking of supernovae that are more than 50 megaparsecs, so I don't know if.
To be checked, yes. I don't have it back of my head, but no.
Like I think that multi-messenger astronomy for together with the LSST in supernovae case is going to be very hard because of the detect horizon of the gravitational wave interferometers and the neutrinos. So like in the most promising cases, Vera Rubin will be saturated, most probably.
Okay.
One more last question. If not, we thank the speaker again and all the speakers of the session, especially for being on time. And the next session, so the program says coffee break, but please, we also take the conference picture first. So please resist temptation of grabbing a coffee right now and leaving the room. Please follow our Institute photographer, Ines, just in the back. Just for the photo, I think we'll go out to the left, but please follow her, and then we will come back to enjoy coffee and refreshments, and we will reconvene at 11:15 for the session. Thank you.
Hello, is this microphone working? I think so. This one is also working. This one is so, whoa, this one is loud. Hello.
No, it was from here. I thought that we were sharing. So this we can close because this is so Alicia. So keep this open. So it's in the downloaded file. So descargar. But what I was doing is just that you open, it opens in the browser.
Okay.
Full screen is here.
And then
And
that's present.
then she will finish. So you will
Exit. Yeah.
and then Alt tab, this one
Alt tab.
will get you here. Or you can do that here or here.
Okay. So it's just a folder. Can I quickly try it? Just to
Yes, sure.
see. So it's there. Okay. And then to go back, you do the same again?
Yes, you can do the same. But if you will open, then it will open automatically, right?
I see. Okay. Yeah.
Make it full screen.
Yeah. Yes. So are you gonna do this later or do you want me to?
No, I think Paul wants you to do that. No?
It's easiest. Now, you have the program, and while we are when the session on speaking is coming to an end, you just check for the next talk, and you close this one and open it. So then we don't need to run around and stay here. It's just yeah. Okay, and then when we get here for now. Let's continue with the session. Please find your seat, your table. So it's my great pleasure to announce Alicia Lopez, a fellow Ramon y Cajal Fellow, with an invited talk on transient TeV astronomy with the Cherenkov telescope on the Canary Islands. It is yours.
Okay, so hi everyone, and first let me thank all of the organizing committee for having me here, especially because today I'll be talking about ground-based gamma-ray astronomy, which is a topic that I know that many people here in this conference is not really familiar with. And I know that many of you would be wondering, like, why do we care about gamma rays, no? And the basic answer is that because by doing ground-based gamma ray astronomy, you get access to the most energetic counterpart of many of the sources that you are interested about. And the thing is that in the Canaries, we have one of the only 3 places in the world where you have arrays of Cherenkov telescopes, like the ones we see in the image. Look at those beautiful telescopes that we have in El Roque Los Muchachos. And so today I'm going to put into value the transient science that we do with these telescopes. So just very briefly, many of you already visited here the IACTEC, so you heard a little bit about gamma ray astronomy. So basically what we do is to detect gamma rays indirectly by studying the products that are generated in the atmosphere once a gamma ray enters and interact with the particles there. So you see that there will be a cascade of secondary particles that are traveling faster than light, and due to the Cherenkov effect, they will emit this bluish light that peaks in the ultraviolet, and it's very dim and it's very fast. This Cherenkov light lasts a few nanoseconds. So this would be like the schematics, no? So you have the gamma ray that enters, it produces a cascade of particles that emit the Cherenkov light, and that's what we detect with our telescopes. So these telescopes are called like Imaginer Cherenkov telescopes, so I will be saying Cherenkov telescopes for abbreviation. And when we talk about gamma rays, we normally don't speak in terms of nanometers or wavelengths, we talk about energy. So just as a reminder, if optical wavelengths have energy of around electron volts, I'll be speaking about gamma rays that are in the tera electron volt and tens or hundreds of tera electron volts, okay? And with other kind of experiments from ground, you can even detect peta electron volt emission, okay? So we are really going to the higher end of the electromagnetic spectrum. So the current generation of Cherenkov telescopes, it's about 20-something years old. We have the HESS telescopes in Namibia, this array of 5 telescopes. Veritas in the US, an array of 4 telescopes. And in La Palma, right now, we have the MAGIC telescopes, which is a couple. So all of these 3 arrays were born as experiments to really test that the technique work, that doing stereoscopic observations with big telescopes, that we would be able to detect many sources. And now we have proof that astrophysics from ground, it's really a fully developed discipline. And so now we are building what would be the future observatory for gamma ray astronomy, the CTAO, the Cherenkov Telescope Array Observatory. And why should you care about this? Because it will be an open observatory, so you will also get access to it, okay? So if you're interested in a supernova or in some kind of binary system, you could be able to apply for time. And the thing is that in La Palma, we are building the Northern Array, okay? So in La Palma, we will have 4 large-sized telescopes, 23 meters in diameter, and we aim to have at least 9 medium-sized telescopes, 12 meters in diameter. But that's only the NODEM array that you can see down on the right. In parallel, in Chile, we will also have an even larger array of telescopes. There will be large-size telescopes, medium-sized telescope, and a small size that are like 4 meters in diameter. So small, but not that small. Okay. So in the array in Chile, we'll have about 50-something telescopes in what we call the alpha configuration. So what I'll be showing here today is basically some of the results that we are getting with the telescopes that we have in La Palma. So the 2 MAGIC telescopes, remember those that were born like an experiment 20 years, and the first large-size telescope of the CTAO Observatory that was inaugurated in 2018. So those who were in IACTEC yesterday, you can look on the right, this big telescope of 23 meters, and you can actually see the camera reflected there, no? Like the cameras we have there. So our transient program has a lot of different kind of transients, okay? You see like a lot of extragalactic events, GRBs, tidal disruption events, core collapse supernova, fast radio bursts, but we also have a large galactic program. So we are interested in magnetars, especially because of potential connection with FRBs. We also are targeting many kind of binary systems because maybe you're not aware, but many binaries, especially those that have a compact object, are also very high energy emitters. And for example, something curious, if you're familiar with microquasars, you know, microquasars, they go outwards, no? They're basically in quiescence and then they go flaring. So for example, in the TeV domain, we detect microquasars as persistent sources. We detect the emission between the jet and the interstellar medium, but we have not yet detected microquasars in outbursts, okay? So there is still many of these transient sources that we really are trying to catch in the TeV domain. So today I'll be basically be focusing only on 4 types of sources, like as you can see also in a multi-messenger context, and why I'll be focusing on novae, gamma ray bursts, gravitational wave searches, and neutrino, because these are sources that either have been found to have a TeV counterpart, so a gamma ray counterpart, or because we have seen strong hints, and I don't have time to go through all of this. So as I mentioned, I'll be talking about results with the telescopes that we have in La Palma, MAGIC and LST, and then very short introduction to future prospects with CTAO and ASTRI mini array that you will see later in the Teide Observatory, okay? So one of the most recent discoveries is actually the detection of a very high energy gamma ray counterpart to novae. You already know very well, we have discussed in this workshop about novae. So basically, just something that it's important for us is that remember that there are typically two kinds of novae depending on the type of the companion star. You have classical novae where you have a main sequence star plus a white dwarf, and a symbiotic novae when the companion star is a red giant, okay? So in the case of symbiotic novae, some of them show repeated outbursts. They are so-called recurrent novae. In the galaxy, we have around 10 of them. And in the case of classical novae, they do not show recurrency, or it may happen that just the recurrency times are very long. So normally you see a classical novae and you don't see it going off again. And the thing is that novae, we know that they are gamma ray emitters for some years already, but at lower energies, because the Fermilab satellite, that is the one there on top, that detects what it's called high energy gamma rays, so in the mega electron volt band, so slightly lower, already detected several novae in the 2010, 2014. So Fermi has already detected both symbiotic recurrent systems, so with the red giant, and classical systems. But if you look at their spectral energy distribution, you see that the energy just gets up to 6 or few giga electron volts. It doesn't get at higher energies. So for a very long time, the community has been trying to detect novae at higher energies. And we were lucky enough already with the Ares of Fiuki that it went off in 2021. It's a symbiotic recurrent system. It has a recurrency period of about 15 years. And for example, in this case, the Gaia distances are very important for us because in this system it was not really well known what was the distance to this binary. And the source was detected by HES in Namibia and also by MAGIC and LST-1 telescopes in La Palma. And the thing that I didn't mention is that gamma rays, they are produced via non-thermal processes. So gamma rays are produced because you have particles interacting, okay? So when you detect gamma rays, you can have idea of the particle populations that you have in your sources of interest and the mechanisms for acceleration and for interaction. So if you look at the plot, you can see here the spectral energy distribution of the points we measure with Fermilab, the satellite, and then with MAGIC. And you can see that we tested two scenarios, the hadronite, so accounting that protons are the ones that produce the gamma rays, or a leptonic scenario in which you have electrons that via inverse Compton produce the gamma rays. And what we saw is that the hadronic scenario is the most likely scenario for the gamma ray emission that we detect. So this means that novae are proton accelerators, okay? And this set a new type of very high energy source. So now we do not add another source to the list. In total, there are like 300 sources of TeV gamma rays. So quite some, but not too many. So now we have identified a new type. So now we can say that novae are also TeV sources, okay? And we can say that it seems that protons are the one that produce this emission. And this is also important because you know that we have what we call the cosmic ray C, no? And this also helps us to say, okay, so what is the contribution of novae to this cosmic ray spectrum? What we saw is that it doesn't have a global impact, but that locally novae, in the case of, especially in the case of recurrent system, you can have these local bubbles of enhanced cosmic ray density, which can measure even few parsecs away, okay? So they don't have a real impact in the overall cosmic ray spectrum, but locally they can be very important. And you can see that the emission that we measure on top is MAGIC, on the middle Fermi, and on the bottom the optical emission. You see that we detected the emission in the very first 4 days. Then we have a break because there was a very strong moon. We could not observe because when there is a strong moon, there was a Kalima episode, so dust coming from the Sahara. And then after that break, we did not detect the source anymore. And and for example, LST-1, that is in the commissioning phase, also observed the event. And you can see here the blue points is LST-1 together with MAGIC and HES data. And you can see how the spectra over time hardens. So this means that that your emission is actually shifting to higher energies as the days pass by. So this means that even that your protons are accelerating. This is what more or less what Juan was saying yesterday, that that for intensity interferometry, we really need to be fast to check the emission in the very first hours. But for gamma rays, you actually see that it seems that there is a hardening. So even if you don't catch it in the very, very first minutes, hours, etc., you can expect that the emission goes to higher energies as days pass by. And of course, the Corona Borealis, we are waiting for it because since it's much closer than Ares Ophiuchi, we can expect it to be between 7-10 times brighter. So for us, it would be really, really an important event because it would let us know more about these systems. And as Juan mentioned yesterday in the intensity interferometry talk, we also do intensity interferometry with these telescopes, okay? And we expect to measure how the nova expands. So check his presentation. And then let me jump to another type of source. So gamma ray bursts, you know that basically you have a short GRBs that are due to neutron star mergers and long GRBs they are due to massive star collapsings. And of course, we want to catch them. So actually, both MAGIC and LST have been designed to be very light, to be able to repoint anywhere in the sky in about 25 seconds. So imagine you have these giant telescopes of about 20 meters in diameter, but that they only weigh 100 tons. compared to Gran Tecan, I think Gran Tecan is around 400 tons, okay? So, and these giant things, they move in 20, 25 seconds anywhere in the sky. So, for example, this GRB 190114C was the first GRB ever detected in the TeV domain. And if you look at the timescales, so you see that we received the alert. The alert was by Swift was issued 20 seconds after the GRB happened, and like 50 something, not even a minute later, we were already taking data, and the signal disappeared like 20 minutes later. So for us, being able to repoint, and not only repoint, but to prepare the telescope with all of the loading the trigger tables, etc., it's really important. It was key for this discovery. And there you can see what the multi-wavelength flux versus time looks like. And you see the prompt emission, and you see that magic in green, what was the afterglow emission. And here, if you see the SED at different times, like below 2 minutes and 2-3 minutes, if you correct it for the extragalactic background light, because your photons, your gamma ray photons get absorbed, okay, as they travel through us. What we saw is that there is a second emission component in GRBs that is due to what is called synchrotron self-quantum. So it's inverse quantum over your synchrotron photons, okay? And well, since this GRB, there have been like a total of 5 GRB detectors in the TeV domain by Hess and by MAGIC. One key source is also GRB, this GRB that is the farthest TeV source ever detected at 1.1 redshift, also with the synchrotron self-quantum model proposed. And recently, we also observed what is called the brightest of all time, GRB 221009A. It's a really rare event. The rate is supposed to be once every 10,000 years. It was observed worldwide. It saturated many instruments, and this event was even measured above 10 tera-electron volts by some other kind of gamma ray detectors. The thing is that the GRB went off during the full moon break. So when there was full moon and not a single Cherenkov telescope in the world was able to observe, of course it went off. But we really pushed, and on the following day, we sent people to La Palma, and we did observations in these really challenging conditions with the LST-1. You can see there the mark, like a very strong moon in orange, a strong moon in yellow, and then dark data. And luckily, because what we saw on our first night is that very strong hint of detection. So we normally claim that there is a detection if you have a significance of 5 sigma or 5 standard deviations. There is like 4.1. Many people in the community already with 4 sigma, they claim a detection, but we want to be cautious, so we said it's a strong hint of detection. And here you have the SEDs at different times, and this is the full picture of the event with different wavelengths. And even if we don't detect anything, we can help set some constraints on the emission scenario. So LASO, that is a particle detector that is located in China, here seen in gray, sees that there is a jet break here at these times 700 seconds that is independent of the energy and of the wavelength, and this supports the evidence that there is a structured jet. So you have first a very narrow jet with an opening angle of 0.6 that produces your X-ray emission and the emission seen by LASO, and then the emission that comes afterward that has a different spectral index comes from a wider outer jet. And with our upper limits, we can help constrain a little bit this scenario. And then gravitational wave counterparts. Well, when there was this unique event, it was not visible from the northern hemisphere. Hess observed, and they managed to to put some constraints onto the TV emission. MAGIC and also has managed to observe the region above 100 something days later, but we also we also put upper limits. And something that is interesting is that we observed a short GRB a few years ago with MAGIC, and we saw a hint of emission at 3.1 sigma. And actually, this GRB was later associated to a kilonova. So that's like the strongest hint we have to something that could be associated with a kilonova. But we have this transient handler in MAGIC and LST that really tries to optimize gravitational wave observations. And it goes for automatic repointing, and we are trying to optimize the pointing strategy to really cover the area. And for example, during this observational round of LIGO Virgo Cagra, since there have not been like neutron star alerts, we have been following some black hole alerts just to see if because you can maybe potentially have some disruption, something that is disrupted near the black holes, and then you can potentially have some emission. And then a few years ago, we found some neutrino gamma ray connection. So imagine that you have an AGN that has a jet, and in your jet you have like protons and neutrinos and gamma rays that are accelerated, and they come to Earth. IceCube, that is this neutrino detector in the south, in the Antarctica, has detected dozens of these very high energetic neutrinos. And in 2017, there was a neutrino of energy of about 300 tera-electron volts that it was found to be coincident with the position of a flaring blazar, this TXX0506. And both Fermi and MAGIC observed the region, and you can see here the position and the areas. And actually, we detected gamma ray emission. So this was the first association of a high energy neutrino and an extragalactic source. And you can see there the SED at different wavelengths, including also the MAGIC and the Fermi points. So we saw that there is indeed this spatial in this temporal coincidence. And just to start finishing my talk, to wrapping up, so as I mentioned, we are building the CTAO Observatory. Of course, we have other scientific cases, as I said, but those are like the highlight of the last few years. And okay, so this is the image of what we plan to build, and this is how things are going. Indeed, this is a bit obsolete picture already. So you have the two MAGIC on the background and the 4 large-size telescopes. This was like in May or August. I don't remember exactly, but this is the newest picture that we have. As you can see, we already have 4 telescopes with the full mirrors, with all of the structure. The 2 cameras that are there, they will be installed in this 2 that you have on the background, and we hope to finish the installation by end of next year. And indeed, this is going to be the most energetic array by next year, and it will be optimal for transient detection, because if you compare the sensitivity of Fermilab and CTAO is like 10 to the 5 times better at short timescales. No, you see here 1 minute, 10 minutes, 1 hour. So we hope that they are transient machines. And of course, we hope to detect gravitational wave neutrinos and some flaring microquasars, even flaring emission from pulsar wind nebulae. If you're interested, just check those papers there. And today you're going up to the Teide Observatory. There we have this array of 9 small Cherenkov telescopes. So they're like the prototype of the small size telescopes that will go to Chile. Okay, as I mentioned, they are small, but they are still 4 meters the primary and 1.8 the secondary, and they will go and they will specialize in detecting the more energetic gamma rays. Okay, between 1 and 300 tera-electron volts. There is one of them already operational that you see there on the picture. We have been taking data with it for almost 1 year, and by end of this year we will start making observations with 3 of them. But I think that in total there are already like 7 structures around. Okay, so hopefully we will be showing nice results with ASTRI for next year. And even if it was not in the beginning designed to be like a transient factory because really we want to do galactic science. We also see that we can do some interesting things, especially with GRBs. So my take-home message is that you see that we have these Cherenkov telescopes in the Canaries, and that actually Canary Islands is going to become like one of the 2 most important sites worldwide. So keep an eye on CTAO, and if you are interested in gamma rays. And well, that's all from my side. Thank you.
Thank you. Thank you. And we'll have the first question, please.
So my first question is, how discriminative are these hadronic versus leptonic models? I mean, they look very similar, and then they change as a function of time. So there's some degeneracies within them. How can you be sure when something is a hadronic versus leptonic source?
Yeah, that's a good question. Thank you. Because, for example, in the MAGIC paper that we did, actually we saw when you do a statistical test, we saw that the hadronic one versus the leptonic, it was much better. And also the description, it's like more natural what you inject in the hadronic than in the leptonic. When you have a look to what we did in LST, that here with LST, we put the LST data, but we included the MAGIC and the HESS data into the fit. And when you look at the statistical test, they're pretty similar. So in the LST paper, we basically favor the hadronic scenario because what I said, no, in the case that what you need to inject in the leptonic one to get that is less realistic, let's say. But yeah, thank you for the question.
So I have a question about the gravitational waves that you're following up. So are you triggering on every black hole mergers as well? I mean, so you're observing them and trying to find and detection, or?
Yeah, so we are triggering some black hole mergers because, as I mentioned, this run there have not been really So yeah, and we are really targeting the ones that are like how you call it, the region is not too large, so that we are able to.
Yeah. Do you also do any cuts on the distance to the mergers? I mean, or you just try to observe everything and see what happens?
I think that for this we're not doing a cut in the distance, or I don't recall. Do you remember, Andrea? Yeah, exactly. I mean, I think we're just observing.
Okay, interesting. Yeah. Thank you.
Thank you.
Sorry, I have one more. So the new telescopes under construction, they're very wide open. Do you clean them regularly for, like, how does it work? Does the sensitivity degrade as a function of time as dust accumulates, or? Yeah.
Yeah, so they get dirt, they get sometimes cleaned up with the rain. And what we do is that at some point we just change them. I mean, so let's say that the optical quality of our telescopes is not like the one you need in optical telescopes and so. And yeah, it's basically easier to just take them out and put new mirrors than yeah. And yeah, and that way you don't need a dome, you don't need, so it's also much cheaper to build one of these telescopes. And as I mentioned, also the people who saw yesterday the cameras, our pixel size is really large compared to, so you don't really need that. So yeah.
One last question. Pablo, German Center for Astrophysics. Comments about leptonic versus hadronic. The theorists, we would love to see hadron evidence, but unfortunately, all our models cannot see the differences. And usually leptonic is much simpler to explain if you do like really hard theory, but it's more limitation of the theoretical part, not the observation part.
Mm-hmm.
A comment. So in extragalactic astrophysics, definitely I have not, or rarely have seen a hadronic model that was believable, which is why it was interesting that in that case for the novae, the hadronic model was preferred. So, I mean, okay, maybe we need to wrap up, but if you can comment on what physically is happening and what the difference is, that would be very interesting.
Yeah, so basically, well, I don't have I didn't put the plot here. So basically, you can either have protons being accelerated in the ejecta, or you can have for the leptonic one, it would be like inverse Compton on the photons that comes from the photosphere. And yeah, in the both, I think both in the Hess paper and the MAGIC paper, that they were separate papers, we saw that the protons are the favored one. So yeah, but then what I said, when you put all of the data together, LST, MAGIC, and Hess, it's really not evident anymore that statistically speaking, let's say. But okay, we can talk now. Yeah.
Yeah, thank you. Perhaps the next topic break is a good occasion to continue discussion.
Thank you.
As next speaker, we welcome Vera Godunova, and she will speak about the optical variability of the quasar 4C 21.33. Catalog numbers are something fun.
Do you see yours?
Hop on. Did you upload it? Can you click refresh? Question to the log. Do we have to talk?
I think you should go on the Explorer on Chrome. Just download it from Dropbox. Go.
Where's yours? Yeah. We have the specialist for Dropbox, Diego.
Hello, everybody. I'd like to present our poster as a very short talk. So, we analyzed photometric data sets of the flat spectrum radio quasar 4C plus 2135. Which were acquired in 2019, 2025 with ground-based telescopes and tests. We performed multi-band photometry of this quasar during various observing rounds with our telescopes at the Terskal Observatory and at the Skalnate Plesa Observatory. To have a densely colored light curve, we also used data collected by ZTF and AAV zone. We made extensive use of the web server BH tool, and here I'd like to draw your attention to the following point. There are links to other surveys, ZTF, Antares, Atlas, and so. But there are no link to gamma ray observations. If we had both optical and gamma ray observations on screen or on BH-DOM screen at once, we might see delays or absence of gamma ray activity during the time periods. We conducted a detailed light curve analysis. We found a long-term downward trend. Here, during this period, there were two small outbursts, and there was a period, two periods, with two periods of low activity states. Here you can see the time intervals observations we used to analyze the behavior of the quasar. And with darker color, the observations from TESS are indicated, and you can see this observations from TESS not as optical observation, but we have to use programs to process this data. We conducted search for a short-term variability using the F-test. For this analysis, we selected 3 nights, calculated the corresponding values, and found that only for 1 night, the values are close for suggesting variability, the last night. Our observations through filters allowed us to investigate the color variability of the source during the outburst and in quasi-quiescent states. Color indices revealed that there is a redder when brighter trend as observed in most flat spectrum radio quasars. This was analysis of the outburst 2020. Here, analysis of this outburst 2020 and of the outburst 2024, and the colors show the same red with increasing brightness that indicates the thermal emission from the accretion disk. So, we investigated the behavior of the quasar in low activity states, and we found the same redder when brighter trend. So our colleague conducted analysis of TESS data. There was 2 sectors, TESS observation sectors, where our quasar was observed. In one sector, sector 49, we found a short-term outburst lasting 5 hours. We tried to find short periodic variations in test data, but no statistically significant periodicities were revealed. And conclusions, our analysis confirms that the quasar exhibits very weak variability on time scales from hours to days, and color magnitude diagrams clearly demonstrate the redder when brighter trend, which is typically observed in flat spectrum radio quasars.
So thank you. Yeah. Thank you. While the log is checking, we have time for one question, please.
Hi, Nada, Angie. Do you have spectra for this object? Do you have any spectroscopic observations during the flare or during the quiescent state?
No. Okay. We don't have optical spectra. We analyze only photometric data.
Do you know the redshift? I mean, have you checked, is there any spectra of this in the archival?
Maybe in the future.
Okay. So.
Thank you. Yeah, today we got a new notebook and you see we are getting accustomed to the new setup, but with a great team, everything is doable. As next, we welcome Michael Dennerfeld, who's talking about Gaia alert on AGNs.
Yes, thank you very much. I will talk about AGN selections in Gaia alerts. But first of all, I want to put the general setup. You know, there are many ground-based surveys underway from the ground with essentially small telescopes. I will emphasize the first one, the Catalina real-time survey, because it's the oldest one, which gives a long time baseline. And of course, on the right side from space, Fermi, Swift, the recent SWAM French-Chinese satellite, which I will say a word at the end, and of course, Gaia, which is also providing not only exquisite angular resolution, which allows you to see what is happening in the center of galaxies, but also a long-term backwards time scale so that you have an excellent light curve. And I would like to thank warmly Simon Hodgkin and his group in Cambridge for superb work in the alert team. So just as an example of Catalina real-time survey data, they were selecting AGN candidates, but you see the light curves look all the same, and they are trying to model them with microlensing models, which works well 1 out of 10 cases. But I would like to emphasize one there, where this one, which you see a sharp raise and an exponential decay, which is typically a tidal disruption event, but they didn't pay attention to that. And we have about 10 cases like that in the Gaia alerts. So the general Gaia alerts results that I borrowed from Simon's earlier presentation, they're about 13% AGN, which need to be confirmed. I emphasize that all these are hypotheses, which you need to confirm, and about 25% unknown. Of course, you need spectroscopy to confirm all that. So we have gone on by first confirming what they call AGN candidates, either mentioned as candidate QSO in the alerts, or sometimes they say coincident with a GALEX and a WISE source, which GALEX means UV, WISE means infrared, and we have added to that correlation with X-ray data from the Swift serendipity catalog. When you have both UV, infrared, and X, there's a big chance that it's an AGN because the Planck light curve cannot be positive in all these wavelengths. And you see an example on the right side. There are about 400 candidates of that sort. We could get 60 confirmation with a bias selection with those which have an X-ray detection, because it gives more chance to have an AGN. And also, the problem is that the spectral date is usually different from the alert date, because the alert is coming long after the beginning of the rays. I will come to that in a moment. Another example where you see a blue continuum, MG2 lines, H-beta line. Recently, last year, there has been a paper coming out using the BP-RP spectra to try to identify whether it's a quasar or not. You see, this is the light curve from Gaia is one where they start to detect variations with very small amplitude. It has been flagged in Quaya with a redshift, but I would like to emphasize a ridiculous number of decimals. That's what is happening when you use artificial intelligence without a human checking afterwards. You know? So the variety of light curves is very large, not only the symmetric light curves, which I showed you in Catalina real-time survey. Most probably the ones with a lot of random variations are radio sources, but we have also a lot of smoother increase. Again, I understand that the alert is coming long after the beginning because they want to be sure that it's a real change, but that is posing a challenge for the interpretation. I will come back to that later. So you have some flares. On the lower left, this may be a supernova because it's not because it's an active galaxy that you cannot have a star formation and supernovae going on. But on the right side, you see somewhere several flares. It's unlikely in this case that it's a supernova, and we don't know exactly what it is. So these are the kind of symmetric light curves we have, both increasing or decreasing, which need to be interpreted. So what do we have globally? Flares, as I mentioned, sometimes supernovae. Tidal disruption events, we have found a dozen, but maybe a few more. Extreme coronal line emitters, like the spectrum you show here, H-alpha, H-beta, and you see here the complex helium-2 and nitrogen-4, which is typical of Bowen fluorescence. Maybe one or the other microlensing event, but we have no convincing example. And the other question is whether you have dust blobs which are moving in front of the nucleus so that obscuration is changing. And to check that, you would need complementary, not only spectroscopy, but complementary infrared data and X-ray data, which we don't have at the moment. The most interesting result we have is a number of changing look quasars. In fact, in the literature, you find now two terms, changing look or changing state quasar. It's the same thing, but changing look is when you assume that there is something changing in front of the object, like obscuration changing, and they call it changing state quasar when you assume that something is changing in the central black hole. But of course, we have no clue yet whether one or the other is happening. So here is a typical example. You have the light curve on the left, the Gaia alert. This is the reference spectrum from the Sloan digital survey. You see a small, broad H-alpha component. And when we take a new spectrum with the Nordic optical telescope, you see that the broad lines are becoming much stronger. So that's a typical changing look quasar. Into the image here shows you the reference spectrum at the bottom, which is a liner from the Sloan digital survey, and directly at the checkup screen, directly at the telescope, you immediately see that H-alpha and H-beta become much broader. And so we have about 50 new clear changing look quasars, probably 30 more, which we need to measure accurately to be sure that the change is real. And what is clear is that when you have the broad lines appearing, the blue continuum is becoming stronger also. But of course, we have a bias in our selection because we are working with 2-meter class telescopes, and so we need to have relatively bright objects. So we are preferentially concentrating on objects which get brighter. And so, of course, then the broad lines appear and the continuum gets bluer. But we are now following a certain number of objects to see what is happening when they go down again. So as I said, difficult selection. On the left, you have a typical light curve. So we say, oh, okay, maybe this one is going down now. We will do it again. But well, no, it's still not going down. No. And the lower left, you see one which is decreasing. So that could be, it cannot be a microlensing event. That can be a moving dust blob in front. So we want to do it again, but well, the light curve is going down again. So maybe it's a binary object. We don't know. So because we have limited telescope time, we have to select object, and it's not always easy to get the best ones. So what is the problem with changing look quasar? Here you have the classical view of a AGN. You have a central black hole, an accretion disk, which you don't see here, and the important thing is the obscuring torus. If you see directly, the observer sees directly through the hole in the torus, you see the center black hole, you have a Seifert 1. But if you look from the side and are obscured by the torus, you don't see the broad line, it's a Seifert 2. And of course, you cannot have a change from one to the other within time scales of a few weeks or months, because the orientation of the AGN is not changing with that scale. So clearly something else must happen. And so here's another example, view from the side. You have the central black hole on the left, the thin accretion disk here. That's the torus, the dust torus, and the models believe that the broadline region is coming from evaporating gas and dust from the inner side of the torus, which is illuminated by the black hole. So if you have a change of luminosity in the central black hole, for instance, because it accreted a new star or something like that, there is a time delay between the change in luminosity, the time it propagates through the inner region until it reaches the broadline region or the torus, and this is evaluated in days or eventually years. So the important thing is that as soon as you see a change in luminosity of the central black hole, you should get a spectrum and a follow-up and try to find out what is the time delay between the inner change and the change you see in the spectrum. But of course, as you have seen for the Gaia light curves, the alert is coming much later. So we have now to do it reverse, see when it goes down, because the time scale for the alert is often many months after the beginning of the change, and that's too late. Just to tell you that things are not as simple, these are few examples on the right side where you have the central black hole, the little dot on the left, and the big section here is a section of the dust torus. If the gas in gray and the dust in brown is completely homogeneous, there's no way you can see changes occurring in that object. And that's a model which is fitting some of the local well-studied AGNs. And different local AGNs are fitted with a different size of the torus and a clumpy distribution of the dust in brown here. So you can imagine that in a situation like that, the dust blobs surrounding in Keplerian orbits the central nucleus, there can be some moments where there is a hole through the nucleus and you see the central object, and then when the dust blob is continuing, it's obscuring again. So then you can have changes in spectra from broad line to narrow line and vice versa in time scale of months. So you need long-term monitoring. Okay. Follow up. We can do that with any telescope, let's say larger than 2 meters for spectroscopy. I just show here an example which was alerted in the early times as an AGN, but in fact, you see on the left, our spectrum shows just an H-alpha, so it's a BE or a young stellar object. But there are few cases like that where the initial alert was wrong. So. And importantly, in many cases, dormant AGNs wake up. You have galaxies where you don't see an AGN, and then suddenly sometimes broadline region appears because some new fuel has come to the central object. And this is an example, which is 22 CMC. On this diagram on abscissa, you have the time scale increasing, and on the left, on the ordinates, the magnitude. Lower right, you have the classical supernovae. upper left, you have the classical gamma ray bursts, and these AGNs are waking up and settle in the middle of this diagram. So in fact, looking for variations in AGNs or so-called galaxies, you can discover AGNs which were not known before. So it's an excellent tool for that. Okay, I go through that. So I said spectroscopy. Łukasz asked me to say some words about the new spectrograph we have at Haute-Provence Observatory. You see it on the telescope here. It's a folded Cassegrain. I will not enter into the details of the scheme. You have a focal reducer on the left and a parallel beam. And in this parallel beam, you have low resolution gratings, blue or red, high resolution H-alpha, and of course, a series of filters to do photometry. You can do indifferently photometry or spectroscopy. Just to give you an example, this on the left, you have an AGN with a blue setting. You see that the noise becomes worse on the blue side. That's because the CCD response is going down. And on the right side, you have a red setting with T Corna Borealis, where the noise is getting worse in the red. It's not due to the detector. It's due to the fact that you have very strong night sky and OH subtraction remains some noise. And to finish, I show you the French Chinese satellite, which was launched last year. The main thing is a X-ray gamma ray detector, but the important point is we have also a visible telescope on board. So as soon as a new source is detected with the signal to noise, which is larger than, say, 7, the satellite is pointing over there and you get an image, visible image, blue and red of the center, and you can identify whether or not there is a new object in the optical. Okay, so my conclusions is that variability is an excellent tool to find new AGNs. We need a lot of spectroscopic time to do that. And the time scale to react depends on the type of object. As you know, for gamma ray burst, you have to react within minutes. For supernovae, some hours, that's okay. And AGNs are much more comfortable because you can react within 1 day or 2 days. You have time to set up. And as was already mentioned before, the LSST will provide millions of alerts per night. So the real question is, how will you select the ones you want to observe? Thank you very much.
We thank the speaker. While we are setting up the next talk, we have time for one question, please. We have time for one question. Is there a question? One. We cannot use this.
Hi.
No.
Thank you. What? Okay. Nada, ING. I have a question about the
next slide. Yeah. We are way over.
Okay. Sorry. I have a question about the waking up AGNs that you were talking about. What are the typical light curves look like for them?
The typical light curve?
Well, for the waking up AGNs that you were mentioning. How, I mean, what would you see in a spectra or in a light curve? How would you recognize these from, something else?
The light curve is flat, and at sudden it goes up.
Okay, so it just gets brighter.
So there's no variation before.
Okay, yep. And the spectra is just.
Well, in most cases, you don't have a spectrum before, because it's one of millions of galaxies which were unknown.
Yeah. Okay.
Just this point, because again, Łukasz
out of time.
Yes, but Łukasz said I have a minute more to show this because it's a poster which was not. It's to mention.
Okay, you say the magic word, Łukasz.
Yeah,
so
yeah.
Please continue.
It's the French amateur professional astronomers collaboration, where we have set up a series of filters which I think could be adopted by many of you. On the left, you have the so-called Gaia filters. By the way, I don't know whether all of you know, there are no filters on board of Gaia. It's just simply defined by the response of the detector, which is fine in space because it's not changing. But from the ground, it's not possible because for each site, it's different. So we have designed on the right side a broadband filter in gray and a blue filter and a red filter, which are well defined so that everybody, if you use these filters, has the same setup, whatever the detector you use and whatever the atmospheric quality of your observatory. So we have distributed already 50 filters like that to amateurs in France. And those of you who are interested in getting some filters like that, there is a second batch which is being produced now. Sorry for the delay. But,
we thank the speaker again. And the next speaker is Nadia Inahek. Sorry, Slavic is not my mother tongue. And she will talk about energetic outbursts.
Hi, everyone. I'm Nada Ihanet, but in Spain, I know it's hard to pronounce. And I will be talking about energetic outbursts from the centers of galaxies and their origin, which is really similar to what really similar topic to what we just heard in the previous talk. So I was using Gaia photometric science alerts to search for these nuclear flares. So as you all know, Gaia was a all-sky survey since 2014 with approximately 30-day cadence. And as we heard, in total, it published 27,076 alerts. There were many different types from CVs, young stellar object, microlength events, basically everything we've heard in the last few days. And approximately 10 of them are nuclear transients. So for definition of a nuclear transient is that it is connected to the center of a galaxy. So it's connected, it happens in the nucleus of the host galaxy. And these can be AGNs and changing blue quasars, tidal disruption events, boron fluorescence flares, these new phenomena called as ENTs, because I also prefer ENTs to ENT, I guess. But yeah, so one of the main problems is that it's really hard to figure out what is a what is it in the nucleus of the galaxy and whatnot. So here are two examples. Both of them turned out to be tidal disruption events. So that means that they were actually occurred in the nucleus. But just by looking at the image itself, you see this one, you can kind of clearly assume that it did occur in the nucleus. While in this case, we have a galaxy, this blob is a galaxy, and this is the location. So we don't really know if this is center, connected to center, not what's happening. So because of this, there are also nuclear transients could also be supernovae, which are, of course, not connected to the center. They just appear to be really close to it. So that's why I have them here in the slightly further away. So just to quickly go through some of these nuclear transients that I mentioned, and you've also heard some of them today. So changing look AGNs, as it was said in the previous talk, they have a magnitude change. During the change of the light curve based on the magnitude. We also then have, when you check the spectra, we have broadening or narrowing of the emission lines, which really complicates the unified model of AGN that was mentioned before, because the field of view, the field of the AGN cannot really change in the span of 10 years. The second one are tidal disruption events, so which also Priscilla mentioned. So this happens when a star comes too close to the central galaxy, to the supermassive black hole, and the tidal force then disrupts the star. I know that I had a video here, but since it's PDF, I don't want to destroy it. Though I think if I... Yeah, no, okay, not working. But basically, you have a star. This is a simulation. So the star comes to close to the central black hole, and all of these, basically the colors that you see, this is the disruption of the star. So the hydrogen and some helium that gets then accreted around the black hole. This can only happen for the black holes, masses 10 to the 6 to 10 to the 8 solar masses, and they're extremely luminous events and really hot. And in the spectra, they have really blue continuum and broad helium or Balmer lines. And for the longest time, everyone thought that these are, all of them the same, but it turns out that it's quite heterogeneous group. So we recently started classifying them in 3 different classes. So TDE hydrogen, TDE boron, and TDE helium, depending on the spectra here. And as you can see on the left, the light curve evolution. So the faster ones evolve so around 50 days, they go back to the baseline. Some longer ones take 200 days or more. The second, the class, which is one of my favorites, it's called boron fluorescence flares, or BFFs. So these are the flares in the centers of active galaxies, and they show this boron fluorescence. So what we get is, for some reason, we have increase in UV optical emission, and this triggers photons from Lyman alpha like transition of around 300 angstrom of of helium-2, which excites certain stages of oxygen-3 and nitrogen-3. This then leads to cascade of transitions, and we see the helium-2, the most prominent lines are helium-2, nitrogen-3, and oxygen-3. And the interesting part of this that it was well established in planetary nebulae and X-ray binaries, but it was really rarely seen in AGNs. And these are 4 examples of these boron fluorescence flares. I believe now there are 2 more, but I didn't plot them. So you see these really strong helium-2 and nitrogen-3 emission lines. And as you can see in the light curve, so this is the host subtracted light curve. Just the flare, you see that we have even 1,000 days after the peak, and they're still ongoing. So comparing to the TDs, they're really much longer than TDs. So it's separate class. So what I've done for this study for the in general projects is I did a statistical study on the alerts. So I've done the last time this in October 23. I do want to repeat it again for all of the newest alerts, but I just need time. So I started with 23,639 alerts, and based on what we have in Gaia photometric layers, these pre-classifications, I kept AGNs, quasars, galaxy, BLX, TDEs, and unknown. And this led me then to this number. And then I also cut for the galactic latitudes. And then also based on the comments, so everything that said candidate young stellar object or star or TDE, sorry, not TDE, supernova, I discarded it, and I was left with 4,786 alerts. And because I really wanted to do a study, not just like automatic cuts, I then did visual inspection on all of these light curves. And I kept what I was interested in is, of course, that the target is in the center of a galaxy, that there is small or no pre-flare variability, because I didn't want to have just typical AGN variability, and also non-periodically repeating flares. And important factor here was also that the flare itself or increase has to be bigger than 0.5 magnitude, because this is, again, I didn't want to have normal, typical AGN variability. And I was left with 329 suitable targets. And my plan in the last few years was to get as many spectra for those as possible. So these are some of the examples of the light curves, the flares that I was studying and got the spectra or were kept in my criteria. So you see here, these are all light curves from Black Hole Tom, which was really, really helpful because I was able to have the history, the photometric observations since 2004 from Catalina. So you see that in this case, there was no variability. And then all of a sudden, we had 2 magnitude flares, which then started decreasing for, I believe, 4 or 5 years. Again, this is all much longer than typical supernovae, right? So then we have some examples when there was some flaring before. In this case, I know that this one I didn't see before I observed it. I took a spectra in this case when it was started increasing, and then afterwards it just dropped. So this one was just flaring AGN. And then I have a spectra of alerts that have some small variability maybe, but then slow increase, right? So these are the 4 examples. And then some what I've done for with spectroscopic observation and analysis is that I got spectra from few different telescope and instruments, and so far I have around, here it says 120 targets, but I do believe it's more like 150. Some of them, if I was lucky, they have existing SDSS spectrum. So I was able to compare how the change, the spectral change occurred, what we saw. So for the analysis, I tried to do classification. So what is the mechanism driving this explosion, this flare? I determined the redshift, then brightness at the peak to get the total emitted energy, which was of course limited by the photometric observations that I had. So I don't have, for majority of them, there's no swift observation. So there's really just a limit on the total energy. And then I also determined some host properties, so black hole masses, the torus type of hosts. And of course, use of the black hole term was for this really, really great. So some of these are just some of the targets that I had with that I used IDS spectra on INT. I obviously have more, it's just that they didn't fit on the page. So as you can see here with the absolute magnitude, so some of them are, we have absolute magnitude of -26.1, -25. So these are really, really energetic flares. And majority of them are quasars, or at least I classify them as quasars because I didn't see any other signs of either tidal disruption event or changing look because of the comparison. So the ones that I have here, dust toruses, those are all of the ones that have a clear flare also in NeoVise data. So I think that those are, you know, especially interesting, and we can determine more information. So here are some of the examples. So this is Gaia in BZP. You see that there was two magnitude rise in 2 months, and then afterwards it's been declining for 4.5 years. I think now it's also already going towards 5.5. So it's still ongoing. It's really nice. I have few spectra for this, but for me, this one, I did classify it as candidate buoyant fluorescence flare based on the spectra and these nitrogen and helium lines, as I said before. Then the next one, 22 AFT. So we again have 1 magnitude rise in 2.6 months, and then there was, I didn't zoom it in, but basically like around the peak, there's 6 months of plateau, and then all of a sudden it started decreasing, and this all took around 2 years to decline. Oh yeah, sorry, the light curve is here. See, and then the next one, this one, at least to me, is really peculiar. So if someone has any idea, I would be really interested in. There is a symmetric increase in light curve. And when I looked back then here and zoomed in this area, you kind of can see, again, similar shape. But what makes this one really interesting is comparison on the spectra. So here I shifted the spectra together so that you can see that the spectra are actually identical. There's no increase, there's no change, there's no appearance of any lines. So yeah, I'm not really sure what this is, but if someone has idea, please let me know. Then this one, which used to be the farthest one, now I have one which is 3.6, the redshift of 3.66. The problem with such a high redshift is that we only see the blue part. And this one is a candidate TDE just because of the shape of the continuum. So in AGNs, we don't really see this bluer shape. So now the conclusions and ongoing work. So I've got, in the recent 2 years, I've got additional like around 100 spectra. In January was the last batch. So I'm analyzing them and studying. So I do have few new TDs and buoyant fluorescence flares, and one repeating tidal disruption event, which is also really interesting. And yeah, I still have supernovas are still contaminators. We have a variety of different mechanisms driving these flares, and more analysis is still needed. So yeah, that's it. Thank you.
Questions?
So I was really happy to see that you were showing wise light curves In a couple of sources, it looked like it was delayed, but not as much as I thought it would be. 6 months to 1 year is a little tight for dust response. So did you look at whether or not it was self-consistent with the dust sublimation distance and things like this?
So I was using I didn't check it with this, but this is really good point, because what I used it for is to determine the dust torus. So comparison of the peak from device and peak from the optical, I used it for the size of the torus. And this was basically it, what I did with this, but I will check for sure more. But yeah, there was always, I don't think that I have any examples where the delay was years. It was always within a year, so.
Okay, and while we're changing slides, time for one more question.
It's like some of the sources were found of SDSS spectra. I wonder if you have looked for DESI spectra.
No, I didn't, but I mean, I would be happy to talk more about this, because I think I'm not sure how to search for it, but I would really love to do cross-matching or something to check if there's more spectra, because it really is useful to have one from, years ago and then now. So yeah, I will for sure want to check this. Yeah, thank you.
Sure.
Yep. Okay.
We thank the speaker. And the final talk of this session is by Alicia Pucek, I hope that was correct, on new possibilities for BH-TOM.
Yes, hello. My name is Alicia Pucek, and I am a master's student from Astronomical Observatory of the Jagiellonian University in Kraków, Poland. I want to discuss a new possible target for BH-TOM, and they are called strongly lensed quasars. And I use the word new because there is no such classification in the BH-TOM website so far. And here is the outline of my presentation. I will give the history, theory, and why lensed quasars are important. And then I will try to answer why it is challenging to observe them. And then I will give 2 criteria for smaller telescopes. So the requirement that the target should need to be observable using a small and medium-sized telescope. And finally, I will propose some targets. So there is a historical snapshot. Firstly, Albert Einstein showed that the star can act as a lens, but he judged that this event would be hard to observe. Later, Zwicky showed that a galaxy can lens distance sources, producing multiple images. And next was Revstar that showed that different images of the same distance source will arrive at different time, and this time delay will prove 2 things: a lens mass and the cosmic expansion, tuning time delay as a way to measure Hubble constant. And finally, the first confirmed lensed quasar was discovered in 1979. And here is the basic of lensed quasar's time delay. Here you can see the variable distance source of the quasar, and here is the observer. Between them, there is a massive object, a lens, a galaxy or the cluster of the galaxies. And because of that, the light is bent from the quasar to the observer, and the observer cannot see quasar itself. It can see only multiple images of that. But those images don't arrive at the same time, and there are 2 reasons. Firstly, is the geometric delay that arises from different path lengths. And secondly, there is gravitational delay that arises because different light paths sample different regions of the lens galaxy potential web. And here is the idea from quasar's time delay to H0. You can see on the right, there is the lensing geometry, and there is the equation for the time delay. Delta t is the different time arrival between 2 images, and it can be taken from the light curves. So this is the clear role for the BH-DOM to produce such light curves. And there are also dependence on the redshift of the lensing galaxy and the geometry, so the image position, the source position, and projected lens potential and the image position. And this ratio of distances is crucial because here there is dependence on the H naught. And I want to highlight this is the answer why lens quasars are important in my opinion, because it is the single step independent way to measure Hubble constant. Here there is one example of the analysis of lens quasar. It was done by Cosmograil, and this project was focused on the cosmography, so a measure time delay from the images of lensed systems. It is the quadruply lens system, and it was observed for over 10 years with several telescopes, all in our filter. And there is the result, there is the light curves. You can see one curve per image, and they have got same intrinsic wiggles, but they are shifted in time, and they are slightly rescaled by magnification. And from such light curve, the time delay was measured, and those are the results. However, lens quasars are challenging to observe, and there are at least two problems. Firstly, this is seeing, because those images are extremely faint and the separation on the sky is only few arc seconds. How to solve this? For example, using deep blended photometry, point spread function fittings, or other more complicated techniques. And this is the thing I want to discuss with you. What would be the option? Also, the problem is the micro lensing by the stars in the lensing galaxy. So the light from one image will hit a star in the lensing galaxy, while light from the other image don't, and it will give additional uncorrelated features in the light curves. And how to solve this? It would be necessary to observe any given system for several years, averaging out micro lensing over a long period of time. And I investigate the BH-DOM network to find how many telescopes can reach approximately 20 magnitudes, and I found 47 from over 150 telescopes. And I also came up with two criteria for me when I was searching for proposition of the lens quasar targets for the BH-DOM telescopes. And the target should be resolvable, so the separation in the sky should be larger than 2 arc seconds at least, and the target should be measurable, so the images should be brighter than 20 magnitudes. And those are the targets, probably. Feedback welcome. To my best knowledge, approximately 300 lens quasars have been discovered. Among them, 8 are widely separated as strongly lens quasars. Widely, I mean the separation in the sky is more than 10 arc seconds. And this is the first confirmed lens quasar. You can see it on the north hemisphere, and you can see also the images are bright and the separation is large, is 8 arc seconds. The second is also the confirmed lens quasar. You can see the coordinates, the brightness, and the separation, and on the cutout there are orange dots near the brighter image, and those are free lensing galaxies. Here is another example. It's also confirmed lens quasar. Again, the coordinations, the brightness, and the separation here, it is the images are closer to each other on the sky. And this is interesting because this is the one that is widely separated. And you can see that the separation is more than 22 arc seconds. A and B are the lensed image, while G1 and G2 are the lensing galaxies. I wanted to also show you some candidates for being lensed quasars, and I took it from Gaia Focus Project release. In this paper, they showed 49 most promising targets to be lensed quasars, and among them, I found 15 that met the criteria, so the images are enough bright and the separation is enough large. And I want to just show the few. This is first candidate. You can see it's quite faint, but the separation is large. Another example is very similar, and on the cutout in the middle, you can see orange dot that looks like the lensing galaxy. And this is another example, the candidate. Here is the coordinates, the brightness and the separation here is quite large. And also in the middle is something that looks like a lensing galaxy between the images. And here is the last. And you can see the same things as well. And I want to say that those were just the candidates, and the spectroscopic measurements are needed to tell if those candidates are true lens quasars or not. And to summarize my talk, I tried to discuss whether strongly lensed quasars are a good target for BH-TOM. Each quasar image on the light curve shares the same intrinsic variability, and the time delay between them, it is an independent way to constrain Hubble constant. There are some challenges. However, I show you some targets that fulfill the criteria. And thank you for your attention.
Thank you. We have a bit of time for questions. Do we have questions? This one.
Thank you for the great talk. Are you applying for time for spectroscopy to observe this? Because you said that spectra are needed, right, to confirm. So are you working on this or?
Currently not, and this is the future plan, but it is also the talk on my PhD, and I am the master's student.
Yeah.
Do we have other questions? There's one.
I have a question. What is the cadence requested for those measurements of quasars?
Okay, so from the papers I have read, they said that every few days it is good to observe, because those variability in the quasar is very long. It is like years, so it is good to have a steady campaign with observations every few days.
I know that there is no existing photometric monitoring at these magnitudes, but is there a way to check the older data to see if the objects are variable at all? Because the examples you showed are really nicely variable, but some quasars are more variable than other quasars. So if these ones are particularly quiescent, it would be, monitoring would not be very rewarding, because there would not be those peaks and wiggles to cross-correlate.
This is a great point. Thank you. Yes, it would be necessary, and I will check later. Thank you.
Okay, if there are no more questions, we thank the speaker and all the speakers of the session. And while we are setting up the next talk, we are entering the session on cultural and on Tenerife, basically. And the first talk will be by Juan Antonio Belmonte, a leading scientist, astronomologist, a leading scientist on the culture in astronomy and also on the ranches. And I'm very happy that you followed our invitation to give this interesting talk. We're looking very much forward to it.
Me manejo con esto. And you put me? Yes. Okay, well, thank you for attending the first cultural part of the program of your workshop. I am a researcher at the ISC working on exoplanets for many years in stellar physics, but during the last decade, I have been deeply involved in themes related to cultural astronomy and history. So this is why I'm here right now. So I'm going to tell you who were the Guanches, the scientific quest for the ancient Canarians. So the inhabitants of the island prior to us, who were here prior that we arrived. Most of what I will tell you is snapshots of a book that I published a couple of years ago with an archaeologist, with Nona Pereira, related basically to all these aspects. So the first thing is the name Guanche. What is the origin of the name? It means the one of Achinech. It originally designated only the first settlers of Tenerife, but has ended up designating by extension all the Canarian Aborigines. Although in other islands they had other names. For example, the name Canarians comes from the Aborigines of Gran Canaria, of one of the other islands of the archipelago, that was extended to all the present-day population. The names of the other tribes, you can find them also in the north of Africa. So there is a clear connection of the fact where did they come from. We are almost 100% sure that they came from the northwest of Africa. And the question is, how did they arrive? There are several hypotheses. One of them is that they came by fortune navigations from the near Moroccan coast. Let's say in Patera. Patera are these boats that we are receiving every week coming from the coast of Africa. Or that they were brought by the Phoenicians, or that they were brought by the Romans. These are the three main hypotheses that are normally on discussion. Who they were? They were population from Berber origin, also called Imasigan. So they are whitish people in the northwest of Africa. So they mixed completely with the Castilian invaders in the 15th century during the phase of the conquest. Now they are spread in small islands, like an archipelago of small lands in an Arabic speakers ocean in the north of Africa. But they are still there, no? So we can trace the ancestry, no? To understand what of these hypotheses should be the correct one, we will make a brief a snapshot in epigraphy, genetics, archaeometry, like Canfor 14, historiography, and also in astronomy, our astronomical studies. Related epigraphy, the Aborigines of the islands, the ancient Canarians, were able to write, and they wrote in two different alphabets. The dominant one is the so-called Libyc Berber alphabet, that it was used in all the islands. This inscription, for example, is of Gran Canaria, is one of the most impressive. But there are inscriptions also in Tenerife and even small samples in La Palma. This writing is original from the north of Africa, from the northwest of Africa. I mean, the name Libyc Berber is a connection between the name of Libya for the north of Africa in Greek times and Berber for the population. And then we can compare. We can compare Canarian inscriptions with the inscriptions of the north of Africa. This is what we made in a statistical analysis, comparing many different alphabets all around the north of Africa, from the oasis of Baharilla in modern-day Egypt to the Canaries, and then from the Saharan desert to the Mediterranean coast. And what we have found is here you have different, every letter means a different alphabets. The blue ones are the ones related to the Canaries. And we can see that the strongest connection is with the alphabets that were present in the ancient kingdom of Numidia. Numidia was a very important kingdom in the north of west of Africa, who was there after the fall of Carthage in 146. So with this in mind, we can be almost sure that the people that came to the islands was in close contacts with the people of the Kingdom of Numidia. We don't know exactly from which place they came from, but probably the normal location should be south of Algeria, south of Tunisia, or even Tripolitania in what is today Libya. We can read the inscriptions. I mean, we know the alphabets by comparison with other alphabets of the north of Africa, but we cannot entirely understand it. I mean, the language we cannot fully understand, although there has been attempts to do it. Another important fact is that in the easternmost islands, in Lanzarote and Fuerteventura, they had a second script. I mean, they use a second kind of alphabet together with the living Berber. We called it the living Latin. You will see why later. These are the sort of inscriptions that we have on the rocks. And we have even the alphabetic inscriptions. So we have sorts of Rosetta stones by which we can see what was written in the different alphabets. And considering that, for example, here we have a typical one. You can read Timamasir Aumakuran in the Libic Latin, and then the short description in vertical at the bottom right, you can read Aumakuran, which means the song of Makuran. So basically the same is written in both alphabets. With this, we can disentangle the alphabet for the Latin inscriptions, and we know it was a sort of Latin alphabet. It doesn't mean that the inscriptions are in Latin. They are in a Berber language, but written with a Latin alphabet. So this is one very important fact. Another important issue or another important clue that we can use is genetics. We can study the genetics of the population in both the Canaries and the north of Africa. And you can study different trends. The most normal is to study the Y chromosome, I mean the short chromosome that we males have, and also the mitochondrial ADN, which is only mitochondria, because they are peculiar in two senses. The Y chromosome is inherited only from father to son, and then to grandson, and so on, while the mitochondrial DNA is inherited from your mother. So you share it with all your siblings, but you will not transmit it if you are a male to your child, to your children. But if you have a sister, she will transmit it. So these two important groups, we can study it in both the modern and Guanche population of the islands. And what we learn is that they are very similar. Actually, if you look at the populations as a group, we have almost the same haplotypes in different groups, but with some peculiarities. For example, we have a negroid haplotype in Gran Canaria, which was not present in the rest of the islands. We don't know why. Before the colonization. Today, it is present in all the islands. We have another important group, the U6B1, which is typical from the Canary Islands. I mean, you can only find it here in the Canary Islands, and it was present in the Aboriginal population. Actually, it was present in the majority of the island of La Gomera, as we will see later. There were other groups that today are in all the islands, but that were privatives from the easternmost islands, Fuerteventura, Lanzarote, and Gran Canaria, and then later spread. So different genetic pools arrived to different islands. This means probably different populations coming from different places. We are almost sure of this. Some of the most important haplotypes, for example, this one, I like it especially because it is mine, is the N81 of the Y chromosome, which was originated in the Mediterranean Maghreb some 2,200 years ago, so almost in coincidence with the fall of Carthage, and that is possibly related to the expansion of the Kingdom of Namibia under King Massinissa. A quarter of the Aboriginal population that has been investigated had this male haplotype. Regarding the mitochondrial ADN, apart from this negroid that I told you before, which is very peculiar because it is the haplotype of the most important scholar in genetics here in the Canaries, who is Rosa Fregel, although he is very whitish, but this is hers. There are a couple of them that are interesting. For example, the U61 is important because you can find it today only in a few populations to the south of Tunisia, in people that were Berber speakers until some decades ago. And the most important, as I told you before, is the lineage U6B1, which was present in more than 65% of the population of the island of La Gomera before the colonization, and still is present in 45%. So it means, what this basically means, that the Castilians or the colonizers arrived without women. I mean, there was a very close intermarriage between the people who conquered the island in the 15th century and the population that was located here. So most of the Canarians can be considered as, let's say, hybrids. Regarding astronomy, I will concentrate only one point. We have been doing archaeastronomical studies in all the islands. This is because we know that the Canarians were astrologers. They worship basically the sun, the moon, and other planets, and maybe stars, as their companions of the north of Africa did. And we have some notes on the calendar, so we know that for them the spring equinox was important as the summer solstice, and also that they probably use Sirius as a reference for the control of time of the calendar that they used. We have analyzed several places in all the islands. Gran Canaria is the one who offers the best quality of archaeological sites. There are a lot of sites with a lot of impressive information, archaeological information, and indeed astronomical information. We have places where you have relation or connection with the summer solstice, like Cuatro Puertas in letter A, or, for example, connection with the equinox, like in Roque Ventaiga, where we have also connections even with the extreme southern position of the moon, with what we call the major southern lunar skies. Fuerteventura also has an impressive archaeological milieu, and especially there is one place, Montaña Tindaya, where you have the largest collection of footprints engravings in the world that we have studied and analyzed, and they also have astronomical connections possibly related to the crescent moon and the positions of the planet Venus. So with all this information, we may try to establish a calendar, and we have clues and evidences that the ancient Aboriginals used a calendar, a lunisolar calendar, a very simple lunisolar calendar in which every 3 years they put an intercalation. They add a month to more or less follow the seasons. This is important. Why? Because it means that although they were certainly in contact with the Latins because they picked one alphabet from them, they were not so strong influence so that they still keep a very old lunisolar calendar and not the calendar of Rome that after the Julian reform, it was a pure solar calendar. So this is another clue that we may have. So considering archaeology and genetics and epigraphy, all this suggests that they arrived at the change of the era, so between the 1st century BC and the 1st century AD. This would solve the question when did they arrive. Carbon 14, I mean archaeometry, actually supports this idea. If you consider the best samples of carbon-14, which are the one that you see at the bottom, you can see that there is hardly any evidence of people in the islands before the change of the era. So carbon-14 almost confirms that possibility. Of course, the sample increases along the centuries because the population was also increasing of the first colonizers that should have arrived here at the very beginning. Then the question is, how did they arrive? This is the very big question. We know that it was an organized colonization, since they brought domestic animals, cereals, and fruits with them. I mean, it is very difficult to argue that they were fortune navigations arriving to the islands, because in a fortune navigations, you do not embark with all these sort of items in your boats. So the idea that we defended 3 years ago when we published the book, and that we still defend, is that they were possibly brought by the Romans or the allies, since they did not know how to navigate. I mean, there were not communication between the islanders of the different islands before the arrival of the Europeans in the 14th and 15th centuries. There was no communication at all between the islands at that stage. This would have been the solution right now if a group of colleagues of the University of Las Palmas, led by a young scholar with an ERC, Jonathan Santana, would have not made a whole reanalysis of all the data of carbon-14 and even taken new samples and obtaining new results that in some aspects fit with what I have told you before. I mean, it is very likely that the first colonization of the island was in the island of Lanzarote at the turn of the century. The problem is the corollary or the conclusion that they have got of their own analysis. They have thought that since the islands are visible from one to the other, this is, for example, El Teide seen from Lanzarote, the northeasternmost island. This is Tenerife as seen from Fuerteventura. So you can see the rest of the islands that the rest of the island called them in some sense. And that the colonization was made by the Islanders themselves, that they were not brought by anyone, but actually they first colonized Lanzarote, and then from Lanzarote, they spread to the rest of the islands, first to Fuerteventura, which is the closest one, and then later to the other ones. And that they were in fortunate navigations. This is hardly to believe. I mean, because there is no single proof that they knew how to navigate, even at the change of the era. But there is a very strong school now, led by the University of Las Palmas, with a lot of people supporting it, that they are with this idea that they arrived in fortunate navigation. But then, in the last year, since they published this paper, I have continuously been doing a question that they have been unable to answer me. The question is very simple. If the first island to colonize was Lanzarote and then Fuerteventura and then the rest of the islands, why do you have an alphabet only in Fuerteventura and Lanzarote, the Libic Latin alphabet, and not in the rest of the islands? Of course, you can use arguments, well, because the populations that went to the rest of the islands only use one alphabet. Why? I mean, because the Libic Latin is much more useful to write the Berber language than their own Libic Berber alphabet, because it writes the vowels, and Berber is the vowels are needed in Berber. So this question has not been solved. And the other main problem is that the analysis that they have made locate the colonization of Gran Canaria, which is the best island of the archipelago to develop a culture, because it has permanent watercourse and a lot of different things, was not colonized until the 4th or 5th century AV, which is completely illogical. So this is the situation right now with two hypotheses which are in conflict. Even the Phoenician hypothesis has been recently reversed by another group of scholars. So if you had asked me 3 years ago, I would have told you that we knew the answer of what was the origin of the Canarian Aborigines. Now, my answer would be, we don't know. I am a supporter of the Roman, of the colonization by the Romans of the Allies, but of course there are other groups supporting any other hypothesis, but you need to explain several facts. One is the question of the writing. Another one is the question that the ceramics of the islands are very different from one to the other. You need to explain why there are a strong astronomical connection in Gran Canaria. They have counts that they even plot in what we call the pintaderas. And you need to explain why Tenerife was the only island where they mummified. This was not the case in the rest of the archipelago. So just to conclude, I would like to finish with this sentence with my late Professor Jorge Wagensberg, who always argued that truth in science is simply the most probable alternative which is compatible with the available evidence. We believe that this is ours. Thank you very much.
Thank you, Juan Antonio, for a very interesting talk. And I'm sure there are questions. Let's start here. And then.
Hi, thank you. Very, very. Just to be a little bit mean, I guess. So if the Romans brought the people that were here, why they didn't stay, the Romans? I mean.
Why they didn't stay? Are you sure that they didn't stay?
Well, I don't know. Are you like? Is there evidence that there is also a Roman heritage?
There are evidences of visits of Roman to the islands. There is even the possibility that they had a settlement in the island of Lobos to the north of Fuerteventura. This is still discussed, but this possibility is there. And we know that the Romans moved populations from one side to the other, especially populations that were problematic. And the question is that at the turn of the century, after the annexation of the Kingdom of Mauritania by Caligula, by Emperor Caligula, who killed the last king of Mauritania, the son of Juba II, Ptolemaeus, actually the last descendant of the Ptolemaics of Egypt, there were a lot of rebellions in the north of Africa. And we believe that this was the moment that the Romans decided to bring people possibly deported to the islands. Because imagine that they were brought with different kinds of goods. They knew how to write and read in 2 different alphabets. They were not very low cultural people. They were of the higher status. So I'm almost sure that this is connected with them, because you have the time, you have the people, and you have the opportunity. Why they colonized the islands? The Romans were fishing in these seas for nearly 5 centuries. So it is perfectly possible that they established population in the islands to have a place where camp, take water, take food, and then go, or something like that. So this is the possibility of why the islands were populated.
I was wondering if you can comment, you were showing the genetic evidence for modern people and for the people before the colonization. So I'm imagining these samples are coming from some archaeological sites.
Yes.
So can you comment on how many sites, how many people? And you also said that the samples are very genetically different between the islands, which seems like a very important clue. So I was wondering, what is the sort of number of samples that are going into this conclusion? Thank you.
I actually didn't comment one thing that I was going to comment on that particular slide here. Look at the hierro. The hierro is the one with the H. The one with the, look at El Hierro. El Hierro is the one with the H, okay? If you go to today, El Hierro has basically the same genetic pool than the rest of the islands. But this was not the case in the archaeological evidence. Why? Because the archaeological evidence is small. We only have individuals of 2 different archaeological sites in the island. We have a lot of evidence from Tenerife, from Gran Canaria, not so much evidence, a lot of evidence also from La Gomera, not so much evidence from the islands of Fuerteventura and Lanzarote, also because the population was not very high. But even in that case, the samples are statistically significant. Only in the case of El Hierro, they are not. And there are clear differences, that there are some different genetic pools in some of the islands that are not present in the others. This is quite clear. And there was a mixture. I mean, after the Normans arrived at the service of the Crown of Castile and conquered some of the islands, the 3 largest, La Palma, Tenerife, and Gran Canaria, were conquered by the Catholic kings, but the previous islands were conquered by the Normans at the service of the Crown of Castile. And there was a lot of mixed population. For example, Tenerife was conquered by an army of just 90 Spaniards or Castilians and 900 Canarians. So later on, there was a very strong mix. But at that moment, there were differences in the different islands.
I have a question about calendars. This was just adding the leap month every 3 years regularly because it is not very precise, or there was an astronomical trigger to do this operation, like, for example, it's the disk from Nerbay.
Thank you. It's a very nice question for astronomers like us, I mean. But we have discovered, we are almost certain that they had an intercalary month when they need it. For it, they observed the equinoxes, the solstices, and also the heliacal rising of Sirius, as did the Egyptians 4,000 kilometers to the east. So possibly they had they did astronomical observations. We have places where they were able to do it. We have clear clues that they did it, and this was possibly to establish festivals to control the calendar, and then add this 3rd month when it was needed. I mean, they didn't have such a periodic stuff like the octateries or the Methonic cycle that you had in the rest of the Mediterranean, but they were able to have a calendar that more or less follow the seasons by observing clear astronomical phenomena. We have strong evidences of that.
Final question by Lucas. We can do it this way.
That was excellent, very inspiring. Could you comment on the name of the islands, the Canary Islands? I want to hear it from the expert.
Okay.
Has it anything to do with Sirius, you mentioned a couple of times?
Pardon me? Well, I don't know what happened. Tenerife is the name that was given by the inhabitants of La Palma. Tenerife means White Mountain. So when Alonso Fernández de Lugo conquered La Palma and then later came to Tenerife, he knew he was coming to Tenerife because the people from La Palma that came with him call it Tenerife. The original name was Achinech, which is related with a tribe of north of Africa that were called the Chinichi, that were inhabiting basically the island of Yerba and the area to the south of Tunis. Gran Canaria is simply, it was originally Canaria, and the name came from Canary, which was the name received by the aboriginal population of the islands. It is argued at some stage in classical sources that the name came from the Latin canis, for dogs. This is not true, because we have the tribes of the tribe with the name Canary in the north of Africa since very ancient times. So possibly part of this tribe come to the island and give it the name. So let's say that the origin from the dogs, from canis, is, let's say, an scholar thinking in some way, you say, or imagination. And then, let's say, Gomera is the name of the tribe. You have Gomara in the north of Morocco and in the south of Tunis. You have a place in the south of Tunis which is called Gomera Sen, which literally means the ones of La Gomera. And it's a village there right now. El Hierro, we don't know exactly what is the arrival. Then La Palma was called Baniurae by the Aboriginals, or Benaware, which is also probably the name of the tribe that populated the island. Then Lanzarote comes from the name of an Italian navigator of the 14th century, Lanzalotto Malocello, who was supposed to be established in the island for trading for pigments for the dresses. Fuerteventura is very obvious. Anyone that will go to Fuerteventura will understand the word. Fuerteventura, a strong wind. I have a friend who is a professor at the University of La Laguna that always that we go there, she calls the island Fuerteventura because it is a very dry island, so a strong adventure because it is a very dry island with very strong winds. It is not easy to work there, although it is perfect to take the sun on the beaches. And I think this is all, no? Yes, 7 islands. Yeah.
Well, there's some eighth one. Sometimes it's the eighth one, the ghost island.
La Graciosa, yes, but La Graciosa was not inhabited when the Castilians arrived.
But there's a ghost one as well.
Pardon me?
There's this ghost island that you only see every.
You mean San Borondón? Well, we will not enter on that.
We will not enter, and I would like to thank Juan Antonio again for a very nice talk, and he will. I hope you join us for lunch outside, which is prepared. Last year, when Juan Antonio gave the talk, he was stormed with many more questions, and he hardly had time to eat. So please give him the freedom to at least get a few churros. Yeah, so this is now just a quick announcement. So we will have lunch, and at 14:30 we will leave by bus. A couple of people are on the car. I would like to ask the driver to come speak with me, and we will go up and we will give you the details on. Yeah, there is some more announcement by Anna, but the details about which telescopes we visit when we will do at the observatory. Please.
Yeah, just because some people ask, you cannot leave backpacks here. We are going to close the building at 2:15 or 2:20 when you are supposed to start walking on the bus. I'll start closing doors. The bus will stay up with you, so you will be able to leave the backpacks in the bus while you are walking in the observatory, I think, but you cannot leave anything here. And for the people that came by car, if you put your car inside the fence, you also need to take it out and park on the streets. Like the building will be locked when the bus comes back. So don't leave anything inside the fence.
Yeah, we will have a bus stop perhaps in La Laguna, and the last one here. We will not go down to Santa Cruz. Please bring your badge, because we need to wear a badge at the observatory that identifies you as part of the conference, and will also allow you to enter the bus if we are not there. So you can leave the stuff on the bus. You have a question? Oh, we actually have a coffee break when we arrive.
At 3, not at all.
Is it?
Yeah.